So, good morning and a very warm welcome from the Zentrum Paul Klee to the first Swiss National GAW and GCOS Symposium. My name is Michelle Stalder, I'm the head of the Swiss GCOS office.
And my name is Andrea Rosa, I'm the head of the GAW CH office. We both work at Meteo Swiss in the International Affairs Division and are in charge of the national implementation of these two programs.
Two programs, one event. Why do GAW CH and GCOS Switzerland team up today?
This is a very good question, actually. In a nutshell, we can say that we want to explore how GAW CH and GCOS Switzerland can contribute to improve the observation, description and understanding of the Earth system cycles of carbon, water and energy.
Observing these cycles requires a holistic approach, which implies the challenge to identify and, even more importantly, implement collaborative approaches across the isolated silos of specific scientific disciplines.
After cancelling the symposium in 2020, we were looking forward to a physical event this year. In early summer, caution had us to opt for a hybrid format. As of last week, our Federal Council introduced, starting off today, the compulsory COVID certificate. But we are very happy that none of the participants that are here at the Zentrum Paul Klee to contribute actually had to cancel for this reason. And we have some 130 online participants joining today's event. So all in all, we are over 150 probably over 160 participants that will follow the 2 days ahead.
So without any further ado, we are very happy to call Bertrand Calpini, Deputy Director of Meteo Swiss, Head of Observations and in charge of both the GAW CH and GCOS Switzerland programs. Please, Bertrand, the floor is yours for the welcome address of Meteo Swiss.
Thank you very much, Michelle. Thank you very much, Andrea, for all the preparation, and welcome to all. Welcome to you here in this Paul Klee Zentrum. Welcome to all the participants remote. It's a pleasure to be together. GAW, the Global Atmosphere Watch Program, and GCOS, the Global Climate Observing Program, have already a long history in Switzerland. GCOS, actually GAW started in 1994. And GCOS started in 2006. And over those period of time, so 27 years for GAW, 15 years for GCOS, Meteo Swiss was involved in this responsibility to transfer the money to the right person, doing the right measurement with observation of the traditional atmospheric parameters, but much more, and also including GAW in direction of air quality and more. Overall, if I try to bring all this together, it's about 50 million Swiss francs that have been distributed since that time. You, all the participants in this symposium, deserve the greatest thanks for all the effort that have been done. Actually, it was coordinated by Meteo Swiss. I was a former direct involved person into this program, and today I'm happy to thank all of you for your contribution in this program. Now, the good thing with WMO, the World Meteorological Organization, is that they are thinking in a sort of more holistic approach, bringing together Earth system cycles that include carbon cycle, energy, and water cycle. And this is also, and I think since quite some years, we had this idea of bringing closer together in Switzerland the two communities, GAW and GCOS. Seda is already telling me that I have 1 minute left. I'll do that. So we are together. This symposium is an opportunity to thank for the past, to understand these three cycles and their synergistic approach, and to see ideas and new ideas for the future. The Paul Klee Zentrum is an inspiration place. It means creativity, and this is what we need in this program. I wish you all the best. I will be there for the 2 days, and I'm happy to give the floor back to Michel. Michel, please.
Thank you very much, Bertrand, for these kind and forward-looking words. Now, without the international GAW and GCOS programs, there would not be any GAW CH nor GCOS Switzerland. I am now pleased to introduce the two individuals who represent these international programs here today. That is first Oksana Tarasova from the GAW Secretariat, and afterwards Han Dolman from the chairman of the GCOS Steering Committee. Please, Oksana.
Thank you very much, Michel, for the nice introduction. We are very happy to be here, and I would like to welcome you all on behalf of the Global Atmosphere Watch Program of the World Meteorological Organization. As you know, GAW is now close to the end of its implementation plan, and one of the motivations which was behind the new implementation plan was moving in the direction of providing the science for services. To do so, we organized 3 new initiatives. You're probably aware of them: Integrated Global Greenhouse Gas Information System, which provides services for climate. We have a new initiative which is working on measurement model fusion for global total atmospheric deposition, which looks at the services to ecosystem community, and the Global Air Quality Forecasting and Information System, which provides the services to the health community. And though there has been already quite an important transition and transformation within the GAW program, all of that happened on the background of the transition of WMO itself. So WMO was going through the constituent body reform, which streamlined its bodies, and we tried to align the program with the objectives of WMO and with the new technical commissions, putting better connection with the operational community. At the same time, we have to deliver on the objectives of our implementation plan. So that's been a challenging time, and the symbol of this transition is integration. We need to integrate the infrastructures, the best science, the services all together and look at the integrated approach. And we do it within GAW. We created new groups which are looking at the quality assurance across different domains rather than within focal areas. We look at the network design in a more integrated way. And we look across the domains and we look across the variables. And I'm very happy to say that Switzerland has been actually a bright example of such an integration. Switzerland provides a very strong support to GAW program, both on the side of performing a high-quality measurements, doing absolutely excellent science, helping to build capacity all around the globe, but also going beyond that. Switzerland was one of the 2 countries which is doing the integrated global greenhouse gas information system on a national scale. That's a foundational activity for the whole GAW program. And it's really great that we have such a diverse community in Switzerland working together, and we've seen at the different Landesausschuss meetings that in Switzerland you have different sectors who are doing the measurements, who are doing the analysis, who are developing the models, working together. And this symposium is actually another example where we can look at the synergies and benefits between the atmospheric composition science, observation and forecasting, and the global climate observing system. I hope that we establish better connection between those 2 systems and that both the climate and atmospheric composition community will benefit from that. Welcome to the symposium. Thank you very much.
Thank you very much. Like Oksana, I'm very pleased to be here. It's partly because the Swiss Meteor has always been one of the more reliable supporters of the GCOS program. And we talk a lot about sustainability of observations, and a lot of that depends on sustainability of the funding. And I think Meteor Swiss has been a prime example of that sustainability. I'll say a few words about GCOS and the importance of GCOS. After my introduction, Jürg Lüttenbacher, I think, will say a lot more about some of the specifics of the program. I think what we've seen this summer is a series of disasters that were caused by climate change. I say that explicitly. I know that there is some uncertainty about attributing those to it. But clearly, there are things happening that are exceptional. And to be able to determine whether that's exceptional, I think we need to have long-term reliable climate records. If we don't have long-term reliable climate records, we can't say anything substantial about changes that are happening, but we also can't stay in the trends, changes in the trends I mean, but we also can't say something about extremes. And extremes are getting incredibly more important at this point in time, as we've seen over the summer. So for that purpose, it is really relevant to keep climate observations going in a sustained manner. What we've done in the past is very much looking at, can we detect change in climate? And we now, GCOS is celebrating its 30th anniversary, 20th anniversary next year with a symposium that was delayed because of the current COVID destructions, and there was also this symposium that was a nice replacement for that. And one of the things that I think you will see in the future of GCOS is that we go more towards making sure that the data is being used. Rather than just making the observations to detect trends, we really want to make the link in the whole value chain with the use of that data and how it's being used, for instance, in adaptation programs. So that will be a change that you will see in the next few years. We've introduced climate cycles in our last implementation plan. That was such a success that WMO decided to reorganize on that basis. And I think one of the key things about the Earth cycles is that it allows you to determine whether you really understand the system. You can start using them to make budgets. We'll have some illustrations of that later on, I think, in the program. But also it allows you to detect where parts of your observing system are still missing, and where you need to define new ECVs, essential climate variables, that need further emphasis. We have basically a cycle. It's a bit similar to the IPCC. We determine what is needed. Our science panels, ocean, atmosphere, and land play a very strong role in that. We write those requirements into the implementation plan, and next year there will be a new version of the implementation plan, and we assess against those tasks in the implementation plan how well they're doing. And for that we just issued the status report that I think Jörg will also mention more explicitly. So in short, we have, I think, an increasing relevance for climate observations. What we do within GCOS is try and listen as well to the community as we can, and I hope this is a good starting point, this symposium for that. Redefine our ECVs where it's needed, define new ones where it's needed, but also make sure that the observing programs are running and keep on running. I think we have to play an increasingly important task in making sure that the short-term funding for some of the observations is really extended to periods that the data become useful. So there I would like to stop. As I said, I'm very pleased to be here, and I hope it's a very successful symposium. Thank you.
Thank you very much for these welcome addresses. I liked what Bertrand pointed out to us. Inspiration and creativity is not an exclusive scientific quality. And so let us draw of the legacy that is being represented by this Centrum. We're going to do something very boring but necessary now. It's some housekeeping information. So you all received the symposium flyer with the agenda. The program begins with a high-level opening session in just a brief short of time, and then 3 half-day sessions for each cycle that we are treating. Each of the cycle sessions is structured in a similar way. It starts with an overview keynote presentation, followed by 3 scientific presentations that should summarize and showcase the Swiss activities, followed by 1 presentation that shows the possible and desirable services that can flow out from the GAW and GCOS activities.
And finally, the international experts will moderate a panel discussion with all the speakers with the aim to distill the main messages and recommendations for future developments. We conclude the symposium with a closing panel discussion moderated by Thomas Stocker to reflect the views on main symposium results of the top management of major environmental institutions of Switzerland, academia and the World Meteorological Organization. So we are very much looking forward to 2 densely packed days ahead of us. We will thank all the contributors for their time and expertise as we go along. At this point in time, however, we would like to especially thank the Scientific Program Committee for their work that will remain behind the scenes. So thanks goes to, and this is in alphabetic order, to Julian Gröbner of the Physikalisch-Meteorologisches Observatorium Davos and the World Radiation Center, to Martin Hölzli from the University of Fribourg, to Fortuna Dios from the University of Bern, to Sonja Seneviratne of ETH Zurich, to Martin Steinbacher of EMPA, Reto Stöckli from Meteo Swiss, and Martin Wild from ETH Zurich. They all were essential in putting together the attractive program we have today and tomorrow, and will act as rapporteurs in the session and also handle the questions during the presentations.
Questions. This brings us to a very serious topic. As we are in hybrid format, we need to say something about that. So the questions or interaction of you participants with what is going on at Zentrum Paul Klee with us today. You're all following us on the online tool Gather Town. If you can see us now, this means that you mastered the basics. But you may want to pose questions or comments, interact with other participants or with the speakers. You can do that, as is usual, with the chat function, which you should find on the left side of your screens. Please note that you can chat to everyone, which is the modality you should use for questions to the speakers. In case not all questions can be addressed by the speakers during the session, we encourage you to make use of the 20-minute windows we refer to as Meet the Speakers. After the talk of each session, we will then, and how you access this, we will give you the details when we get there.
And for all of you who are, like us, not used to video gaming, please get support at the help desks located in the virtual lobby just outside the conference main hall. You will easily find maps to navigate around our conference location. And one last point, since we're coming to an end of this information block, please make sure that your microphones are on mute during the presentations and discussions. But enough housekeeping for now. Let's dive into the program right now.
Okay, so without the WMO, the World Meteorological Organization, there would be no GAW nor a GCOS program. The WMO is instrumental for recognizing strategic needs at the global and regional scale, setting standards, and to ensure consistent and comparable observations. Professor Lutherbacher is Director of Science and Chief Scientist of WMO since 2020. His rich CV includes his leadership and excellence in a broad spectrum of climate science and significant contribution to the holistic climate earth science approach, which we chose to follow in our symposium. So please, Jörg, take the floor.
Thank you very much, Michel and Andrea, for introducing me. Thanks very much to be here. Dear colleagues, dear friends, I'm very happy to be here, back to the roots, coming back to Bern, on the one hand, where I was educated, but also to be the first face-to-face meeting. That's really something over the last 1.5 years. So thanks very much for the introduction, and I will give a short talk about the WMO perspective on past, present, and future of the two programs. And I would like very much to acknowledge co-authors of this presentation, especially Oksana, for the very nice introduction before, but also to provide significant input for the slides. And also Anthony Ria, the Director of Infrastructure from the WMO, with his staff, and providing input in terms of GCOS. So you see the two programs are within two different departments at the WMO, but nevertheless there's strong collaboration, some use of synergies, and that's actually what we also do with this reform, the internal reform, to work much closer together to cover the full value chain. And I would like to thank also Greg McCarmichael and Han for the introduction, who are the chairs of these programs. Just to recall about the GAW implementation plan, Oksana was already saying this will come up to an end rather soon. And the talk is, first I will start with GAW, but where possible I will shed some light, some insights already to connect to the other program, which is important. It's not two standalone programs. They have their own focus, of course, but as we heard before, it's also in a name, new activity actually to bring them together on different fields. So what I will try is to start with GAW, some aspects related to GCOS, and then go to GCOS and make also the link and activities that actually close and link the two programs. So the GAW vision is to grow the international network of high-quality atmospheric observation across different time and space scales, and impact science while co-producing a new generation of research-enabled products and service. So it's this full value chain from infrastructure, from research to services, and of course education and outreach. There are a few implementation areas on the left side, and on the right side you see the structure of GAW. So it's about observations, it's about quality management, data management, modeling, reanalysis, and of course joint research activities across the WMO research programs, but also with GCOS and many other internationally activities. It is about capacity development, outreach, communication, and partnership. And the Scientific Steering Committee will establish a drafting team before the end of this year to develop the next GAW implementation plan. So that's the updated organization of the Global Atmosphere Watch. It looks very complicated, but nevertheless it's straightforward, and it really represents the full value chain and the seamless approach of having infrastructure of research services, outreach, and capacity development. So on the left-hand side you see the 3 research programs from the WMO, including GAW. On down, at the bottom, you see the Service Commission that has been established 2 years ago, and the infrastructure at the top of them. And in between, we have the different activities. The GAW expert team making clear the connection to the infrastructure. So you see it's all connected: data management, network evolution, quality control, quality assurance, which is well connected with an advisory committee on services. And then on down we have air quality and health, we have climate action, and we have also the sand and dust storm warning advisory system moved under GAW recently. So you see the whole interaction between the research, infrastructure, service commission providing services, and on the right side we have strong stakeholders. We heard about the essential climate variables in GAW. This is an overview of the atmosphere, land and ocean ones. And on the left side, you see the GAW focal areas, including aerosols, greenhouse gases, stratospheric ozone, reactive gases, precipitation chemistry, and UV radiation. And you see they are all associated to this research composition. We have an additional one on integrated global greenhouse gas information system, IGIS, which Oksana introduced already. And there we have also a few on the anthroposphere. So GAW stations are required to meet the GCOS monitoring principles, and this shows again how close actually the programs are working. The atmospheric composition network design and an evolution. So the observation network evolution follows the RRR process, so rolling review requirements. And GAW supports actually 3 application areas. They are highlighted here in bold. On the one hand, monitoring atmospheric composition, forecasting atmospheric composition, and provision of atmospheric composition information to support services in urban and populated areas. And this is all done in coordination and coordination and collaboration with GCOS. So you see there's a lot of interaction going on. I just want to highlight a few events that have been taken place the last couple of weeks. And the one was the GAW Quadrennial Symposium that took place end of June, early July. There were different scientific sessions with a lot of participants, all remote, online. This was the Science for Service, importance of atmospheric composition in relation to the services, filling critical gaps in observation, atmospheric composition, and pandemics, which support for new health agenda. And there were also a couple of panel discussions, and importantly, which was very well reflected and what people really appreciated very much, it's the inclusion of young scientists and capacity building, including embracing diversity in GAW. And the different reflections and the symposium are on the way for the Global Atmosphere Watch. And for the first time, the team used this hop-in platform in a very short time to set up and use it in a virtual net platform, which very well worked with a poster session, with interactive sessions. So the possibility to meet, to interact, so highly sophisticated, and that's really a good example how a successful meeting virtual can help very well and to interact with the speakers, sessions, high-level sessions, and so on. And GAW is actually collecting all the information from the speakers and the presentation and the recording that have been done online to follow-up survey that is almost ready to launch. There's another event that took place in second part of July. This is the 11th meeting of the ozone research managers of the parties to the Vienna Convention. And background there is, as this slide shows, it's a very complicated scene, landscape of ozone research. There are multiple players in the field due to a long history of ozone research. And what is actually needed is coordination mechanisms need to be revised and reflect in the modern world. So this means just to use synergies across all these activities and don't have too much overlap, and having really a coordination that brings all these expertise together. And one issue that has been discussed, there was right before the meeting a comment published in Nature on the gaps in ODCS observations, but it failed actually to reflect the important role WMO was playing in the past and also current and will play in the future. And GAW Steering Committee feels it's worth to publish and submit a response on this letter. So IGIS was already mentioned by Oksana, and it's the advancing implementation of the IGIS 3s. There are different activities associated to that, and we heard already the very important financial and logistic support by the Swiss government. So it's a close collaboration with the Climate and Clear Air Coalition on a methane flagship initiative, and just two examples, two proposals were submitted on waste sector methane in Argentina and livestock CH4 emission in Panama and Dominican Republic. And there's also work going on with a Green Climate Fund on IGIS feasibility study, which is a part of the preparedness project in Tajikistan, and something similar will be set up or is in preparation for Albania. And last but not least, their proposal address the land use change, forests by IGIS approach that is developed for Armenia for the submission to Swiss donors. And just recently, very successful of Oksana and her team is a big project and a big funding option related to a bamboo project in China. And last but not least, one more thought on GAW about efforts on COVID, which is very important. There's a new paper coming out with multiple stakeholders, academia involved, that actually summarizes the quality during exceptionally low anthropogenic emission conditions, and this will come out soon. And there's also a new air quality and climate bulletin that has been published just last week, and which was very much reflected and helps also the different stakeholders interested to read more in this issue of the 3rd September. Now a few slides on GCOS. So we have different challenges, as has been described by Han already. It's about gaps in geographical coverages. We all know that. Observations of in situ ECVS are consistently deficit, for instance, parts of Africa, South America, Southeast Asia. And this has actually not improved over the last couple of years. There were a few regional consultation workshops which have identified the problems, making sufficient observation. It's for sure the costs of sustaining observations, specifically in some areas of the world, lack of planning for foreseeable expenses, lack of trained staff and poor staff retention, and poor understanding of the national benefits of observation. So really, what is the benefit of sustaining this observation for public good to provide services? So this needs to be a lot of information going on. There's also the challenging of sustainability. One issue is the long-term continuity of, for instance, satellite observations, which is not assured. Sustained funding is needed. Some projects are just for a few years, but we need, of course, continuation of funding that makes sure that in the long term we have these important observations. And many other successful projects have not led long-term sustained improvements. And there are a few issues related to that for the improvements in the GCOS status report that will come out before COP26 later this year. It is about the sustainability aspects, about improving or filling these gaps, about data stewardship and support of the Paris Agreement. And one issue is specifically on this Paris Agreement, where GCOS and GAW are working together with many other stakeholders and programs. It's on adaptation, it's about mitigation, and it's about climate science, which is strong interactions with many global players. So these are important new avenues working together. And the last slide I would like to finish. It's really, we talked already, also in Switzerland, but also at the global level, there are different initiatives and ways and thinking how to better link, use synergies between the programs. And the collaboration can be, for instance, the ECV requirements. So the ECV for atmospheric composition, for instance. So there's a lot going on, linking the two programs on joint application, standards formats in space, specifically for satellite, but also in situ measurements, bring them together. There's a joint task team between GCOS and GAW experts established, which provide the requirements for GCOS application area, GAW application area, within the OSCAR RRR, and there's also to ensure that name definition requirements of the ECVs of atmospheric composition are consistent across the GCOS application areas. And finally, there's also input of GAW within the AOPC, which is produced by an ex-officio member of AOP nominated by GAW. And there's also important aspects in collaboration and plans within the network, collaboration between the different, at working levels. There are links between GCOS reference upper air network and GAW. So there are many activities going on also in the future, and I'm very happy that we bring them also together in some aspects. With this, I would like to thank you very much and wishing you a good day and looking forward for all the discussion during these 2 days.
Thank you very much, Jörg, for this keynote address on behalf of the WMO. It's impressive to see the breadth of the issues that WMO has to coordinate around the globe. So questions can be posed via the chat function in Gather Town, and they will be handled by our scientific program committee and passed on to us on this device here. So we encourage you to make use of that.
So GAW and GCOS are a major provider for observation-based information for the Intergovernmental Panel on Climate Change. Therefore, it is my pleasure now to introduce Sonja Zenevi-Ratne, professor at ETH Zurich, to the stage. Sonja is an author on several IPCC reports, as well as lead author of the IPCC special report on 1.5 degree global warming. She's also currently coordinating lead author of the IPCC 6 assessment report. Please, Sonja, the floor is yours.
Yeah, thank you very much, Michel, for the introduction. It's a pleasure to make this presentation. I was also part of the organizing committee, the other members, and asked me to give this presentation, so it's a pleasure to give it. And now what I will present is the IPCC perspective, especially looking at the last IPCC report, so the AR6, where we see really the importance of observations both now and tomorrow. So, as mentioned, this AR6 report is still in the work, but the first part has been published. It's the contribution of the Working Group 1, which was released on the 9th of August 2021. You can find it online. And I will provide an overview of some of the evidence we have on observation and where we see that having continued observation is particularly critical. I think I like this FAQ in the chapter 1 of the AR6, which is showing what are the evolution that we can see from the status of science in the first IPCC report, 1990, up to the latest. In terms of the understanding of human influence on climate, Han also mentioned it, for instance, for attribution of single events, but in terms of global warming, in the first report, it was suspected. Now it's an established fact. So the conclusion of the IPCC report is that it's unequivocal that human influences basically contribute to global warming. In terms of observations, you see that there have been also a large improvement of the databases, and that also explains why we have so much more confidence. At the time, there were just about a bit less than 2,000 stations available for land surface temperature. Now we have about 40,000 stations. So just to show you a few main conclusions regarding observations in the last IPCC report, I think the first part, obviously, is what do we know about observed global warming? What is the level of evidence right now? And as you can see, we clearly see from the last decades this increased global warming, and obviously observations are essential to monitor the evolution of human-induced climate change. So we know from those observations that we already had 1.1 degree of global warming in the time frame 2011-2020. Some other estimates for the single year now shows actually maybe already a warming of 1.2, but for this decade it's 1.1 degree. The warming rate is unprecedented in more than 2,000 years, and the temperature level is unprecedented in more than 100,000 years. Another important application of observation is, of course, in combinations with models. That's particularly the case when you're interested in attribution. So if you combine observations and model simulation, you can look at the attribution of the observed change, and you can see that it's unequivocal that human influence has warmed the atmosphere, ocean, and land. So the best estimate of human-induced global warming until this decade is 1.07 degree, and that's about 98% of observed warming. And that's a really important message. So it's not only that human influence has contributed to the warming, the best estimate is that basically almost all of the warming is due to human influence on the climate system. Now, of course, atmospheric CO2 concentrations are also key to look at this evolution of the climate system. And included this figure. Actually, this data couldn't be included because they are from May 2021. The main evidence from the report had to be finished at the end of January. But I think it's important to recall that in May of this year, we had a new record at more than 419 ppm. So of course, these CO2 measurements are of key importance to document the further evolution of CO2 concentration. I think it's also important to reflect maybe what is the current situation we're in. I think when I see this graph, it does give me to pose and question what is happening, because we see CO2 concentrations are increasing unabatedly, no matter how many IPCC reports we are writing, and despite the Paris Agreement, the youth mobilization and COVID pandemic. So I think also, in addition, of course, to thinking about how we can measure the climate system, I think we should also reflect that we have a mandate maybe to inflect this curve. That's a figure from the IPCC report, which shows the same evolution up to 2020. And so you see that obviously this increase in CO2 concentration is seen not only in Mauna Loa, but at the South Pole, for instance, and also satellite measurements. And we know also what is the reason for that. These are mostly burning of fossil fuels, so coal, petrol, and gas, and land use changes. Another point where observations are critical is that it shows now the link between the both change I've just shown before. So on the one hand, the change in global mean warming and the change in CO2 concentration. And so both in models and in observation, we see a direct relationship between cumulative CO2 emissions and global warming. And so, as mentioned, this is also seen in observation is very important to support this relationship. So now I want to move a bit to more geographical information. What do we see in terms of observed warming patterns? This is from chapter 2 of the report, and you see that the temperature observation reveal a warming acceleration after 1970s, so basically since 1981. And I think that's another important point, that the situation is actually getting worse. If you want to look at where maybe we are missing data in terms of temperature, this is shown with a white pot on the map. And actually the situation is not too bad. You see that in most locations since 1981, we actually have data with very few exceptions. An important point in terms of the evolution of observed warming is that land warming is substantially larger than global warming. So we are at 1.59 degrees, so it's much larger. Now, we have heard from Han also about extremes, and that's important also to look at the evidence. And I would say in the last IPCC report, that's actually an area in which we have had much more evidence. It was also presented in the chapter I coordinated together with Subin Zhang. And so, for instance, this is one of the maps in the SPN, which is showing in which regions, here we are looking at AR6 regions shown with hexagons, where we can see that there has been an increase in hot extremes. I think the main message here is that basically it's virtually certain, that's the main conclusion, that hot extremes have become more frequent and more intense across most land regions. You see that basically almost all of those regions are showing an increase. And maybe what is interesting is to also to look at those hexagons which are with hatch. Here it shows maybe at white or gray. Basically, these are regions which either we have a low agreement in the type of change or limited data or literature. And you see that there are really only very few regions where this is the case. For temperature, I would say the situation is quite good in terms of observation. Now, in terms of observed changes in precipitation, on the left, I've shown changes in mean precipitation assessed in the report. You see that in most locations, we actually also have data from precipitation, so that's relatively good. I've also included the map for extreme precipitation, and there you see a lot of those hexagons, which are either whitish or gray, and these are basically regions where we don't really know. exactly what is happening, especially the grayish one, where we say there is limited data. And the main reason for this is that for extreme precipitation, basically we need more daily data. And so that's one area we are missing data, is that we would need better daily data in addition to monthly data. But we have a clear climate signal, as you see, that most of the regions with data are showing an increase. And that's why that's also the conclusion of the AR6, that the frequency and intensity of heavy precipitation events have increased since the 1950s over most land areas, for which observation and data are sufficient for trend analysis, and we have high confidence in that. I also wanted to show this map on observed change in atmospheric humidity. I think first results are quite interesting, but also they show that in this case we have quite a bit of missing data, and that's certainly a variable that would be very useful for assessment of changes in heavy precipitation, droughts, or the global water cycle. So in that case, of course, having more data in Africa or South America would be very useful. In terms of the long-term trends, it's really interesting to see on the one hand, the specific humidity is clearly increasing, while the relative humidity is decreasing. So you have a wetting in terms of total amount of moisture, but in terms of relative humidity, you have a drying. So in terms of observed change in agriculture and ecological droughts, in the AR6, we looked at different drought types. And so we have this type of drought, which is called agricultural and ecological drought, which is mostly based on soil moisture deficit, which is one of the GCOS essential climate variable. It was also complemented with other assessments of related measures, such as water balance estimates or precipitation, complemented with evaporative demand in those regions where it's applicable. So the main conclusions here is that human-induced climate change has contributed to increase in agricultural and ecological droughts in some regions due to increased land evapotranspiration, showing that evapotranspiration is really an important variable. It's also an essential climate variable within GCOS. We see in this case that, again, there are several regions showing a drying, but also many regions where the state of basically the change is not so clear, mostly because of lack of agreement. And I think this shows that we also need more reference observations. So the point is that we have different possible estimates, but basically often those estimates don't fully agree. So we clearly need better information there for these changes in water balance in soil moisture. So I want to say a few words about GAW and GCOS of tomorrow. So which new projects and observations would be most critical when you look at the IPCC assessment and future requirements. And here, these are really just some suggestions from my side. I would say certainly in terms of extremes, Han has also mentioned it, we see there is a high demand for information on extremes, and as I've shown, this information is not always the same as for mean. I think we also would need separate analysis for ocean and land atmospheres. We need to better look at that ocean and land heat storage. Karina von Schuckmann is here and will also discuss on this topic. We would also need, I think, better near real-time observations for event attribution. And I want to mention our observations can be critical for the global UNFCCC stocktake. So in terms of the possible relevance of new observations for extremes, I think when you see this figure from GCOS, I mean, it's quite complete. You have a lot of variables that are covered. But it's not really said whether we are looking at the mean of the variables or extremes, and that's actually quite relevant because changes in means can really differ from those in extremes. So for instance, if you're looking at changes in mean precipitation, they are not the same as the change for extreme precipitation. So realizing that basically these characteristics of extremes are quite different is important, and it, of course, need to be better sampled. Another point is also that for some extremes, there are complementary signals that can be captured from a range of variables. So of course, this focus on essential climate variable is useful. For instance, you look at soil moisture, but if you're interested in droughts, it might be useful to basically combine evidence from soil moisture with evapotranspiration, atmospheric humidity, and land hydrology. About the atmospheric conditions of land versus ocean, one point I came also to realize while working on the IPCC report is that we have this separation between atmosphere, ocean, land, and then also cryosphere. And we need to realize really that the atmosphere over the land is quite different from the atmosphere over the ocean. So I would advocate also having a better contrast between those changes that are happening in the atmosphere over the ocean versus land. So as mentioned, there is a much larger warming over the land compared to the ocean. It's about 80% higher. We also have different humidity trends. And when you are looking at global metrics, which are often used when you are interested in the atmosphere, they are mostly affected by ocean statistics, and sometimes they are not really related to what is happening on land. One example was amplified increase of Arctic streams during the so-called hiatus period, which was showing a clear, distinct response over land versus a global scale. So I wanted to mention the ocean and heat storage. So as mentioned, Karina von Schuckmann will talk more about this topic. But I was surprised that when I see this figure here, actually, heat storage in ocean and land is not mentioned. It's really an essential variable, but it is directly related to radiative forcing, and I would say that's very important also in the point I will mention afterwards with the UNFCCC stocktake. About attribution, Han Dolman also mentioned this. Of course, there is always more requests for information on this, and there have been a lot of headlines just this summer, but also the past years on extreme events, where we basically first had the question, is this related to climate change? But then there was also the answer that often some of those events were made more likely or more intense by climate change. And so we see this type of information, of course, is of key relevance for general communication, but it might even have legal implication, of course, if some of these extreme events have been made more likely by emissions that we have had. For these attribution studies, we generally have a good databases, which is based on analysis data and local observation, but for specific type of events, we could need better observations, for instance, for droughts, and there what is really critical is near real-time availability of data, so that you have data readily available just after the event is happening or even while the event is happening. So again, here I think that for some variables maybe we can have some improvement. Maybe that's something to consider within GCOS if you can have better updates for really larger range of variables. And I want to finish with the UNFCCC global stocktake. So obviously it's yeah, I forgot to see in one on UFCCC. So one main point within the UFCCC is that there will be a global stocktake of the Paris Agreement, and the first one will take place in 2023. And the idea is this global stocktake will be repeated every 5 years after that. And of course, the global stocktake will be strongly affected by observation evidence. And so maybe it would be useful to define, for instance, the GCOS contribution in addition to the GAW contribution. So I come to the conclusions. Observations are critical to assess the state of the climate system, in particular in the context of the current accelerating climate change. Based on existing observation and state-of-the-art climate models, the human influence on global warming is unequivocal. And some key areas for GAW and GCOS expansion, I think, include extremes, particular droughts, ocean versus land atmosphere, heat storage on land and ocean, near real-time observation, and dedicated efforts to inform the UFCCC stocktake. Thank you very much.
Yes, thank you very much, Sonia, for this reaffirmative keynote presentation. I think most of us do know that what we do is important, but of course it's always good to get reminded that it is really key also from the IPCC perspective, and also to see what we could do better in the future. I have two questions here on my iPad for you. The first one is from Belén Martín Miguez from WMO, who wants to know, I was interpolated by Sonia's comment about our responsibility to change the curve. Is this something discussed by IPCC authors? Should scientists and programs like IPCC, GAW, GCOS, etc. go beyond providing evidence?
Yeah, it's a good question. So obviously within the IPCC reports, our main mandate is to provide policy relevant information. We are supposed not to provide policy prescriptive information. But I would say as a citizen, when I see those data, when I see the evidence available, especially maybe the CO2 curve, I do question, you know, should we basically be more active? Because obviously we are not seeing an improvement. And yes, maybe in a different configuration, especially with several organizations, so with GCOS and GAW, especially because that's where the evidence comes from. We are seeing, you know, what is not happening or what is happening. And yeah, I could imagine, yeah, maybe it would be useful to find some other ways to communicate clearly. Yeah.
Good, thank you. And I see a second question from Martin Helsle of the University of Fribourg. He would like to know that remote sensing projects are more directly linked to in situ observations on the ground. How can we better approach this?
Yeah, that's a very good point. So actually, I didn't show this. There's another figure from IPCC which is showing that the evidence on observation has improved a lot since 1980. And obviously, this is also thanks to satellite data. And there it's really important that we have this link between ground observation and satellite data. I believe generally this is done. So there are efforts that are in place to try to validate satellite data, but maybe this could be done even more. And actually a point I also thought about when preparing presentations, obviously we rely a lot on reanalysis data. It's kind of what I meant with the attribution part, that often the data that is available is, for instance, reanalysis data, satellite data, and maybe if we had ground data available right away, it would be useful. So often there is some validation, but there is some delay with the validation from ground observation. Maybe that's where I see the main need is having more timely evaluation. Yeah.
Thank you very much, Sonia. I hand over to Andrea.
Thank you, Michel. And thank you, Sonia. So our next speaker in the program is Vincent-Henri Peuc. He is head of the Copernicus Atmosphere Monitoring Service, CAMS, and deputy director of the Copernicus services at ECMWF. He has been involved in the design and development of Copernicus over a decade. Before joining ECMWF in 2011, he has conducted research for 15 years on atmospheric composition modeling and data simulation at Météo France, pioneering in particular air quality forecasting in Europe, a service to society which gets increasing attention and recognition. We are extremely pleased to have Vincent-Henri in our symposium. Due to travel restriction to and from the UK, he will be with us online. His talk has been pre-recorded, but he will reply to your questions live afterwards. So please roll Vincent-Henri's video now. Thank you very much.
Good morning. I'm sorry I'm not with you live, but I'm connected. I'm very happy to present you some of the updates on our Copernicus services and their connections with the WMO GAW and GCOS programs and the Swiss community. First of all, I want to say that it's a very important day for ECMWF. We are and we've been all the time an international organization. But today, our Director General, Florence Rabier, is opening our new offices in Bonn. So this will be the base for, or the center of gravity for our activities that are operated on behalf of the European Commission, particularly the Copernicus and the Destination Earth programs. And also tomorrow, she will be traveling to Bologna to open our new data center, where our new supercomputer has very recently been installed, and the offices are also inaugurated tomorrow. So very important days in the history of ECMWF. There was also a very important milestone regarding our contribution to Copernicus this summer. At the end of July, Florence Rabier and the director of the DG for Defense Space, Timo Pessonen, agreed a new contribution agreement for ECMWF to continue implement the Copernicus Atmosphere Monitoring Service, CAMS, and the Copernicus Climate Change Service, C3S, for the next 7 years. This comes with a very substantial budget, CAMS 170 million euros, and C3S 241 million euros. And immediately, I want to say that CAMS and C3S are not an ECMWF alone venture, but the services are implemented through a large number of contracts. Actually, most of the activities are not done by ECMWF, but by our contractors. And in the first phase of Copernicus, they came from 42 countries, I think, to deliver the different information products. In addition, there was another good news during the summer, as ECMWF was selected again to be the computational center for the Copernicus Emergency Management Service, operating it until 2027. So we have a number of years in front of us to continue implementing the services. In a nutshell, CAMS is about atmospheric composition, providing consistent and quality control information regarding air pollution and health, solar energy, greenhouse gases, and climate forcing. And C3S as to provide authoritative information about the past, present, and future climate in Europe and in the rest of the world. And a very important feature of Copernicus, which probably most of you know, is that the data policy is so-called full, free, and open, meaning that anyone in the world can have access to these data sets and information products and make use of these for whatever purpose, academic, public, policy, or commercial. To answer the question of the day, I started with a slide to give a little bit the traditional view of how the two GCOS GAW and C3S CAMS interact. GCOS and GAW and WMO in general set the global vision and the framework. Importantly, establish requirements for, in particular, developing applications, and in discussions between the countries represented in WMO to draw global plans for implementation. Conversely, as services in Europe, we can contribute to this global implementation plan by bringing a number of contributions to the activities, and also by contributing to expanding the science and developing the applications in the relevant domains. So I would say that this presentation is slightly traditional, and actually the lines, as I noted in the middle, are shifting quite a bit in a positive way in the context of the WMO governance reform, with the lines being a bit more blurred, and WMO and GCOS and GAW going further into the area of the applications, which gives an even more important role to activities like C3S and CAMS. Example of how this works in practice, for instance, the requirements of GCOS in terms of ECV datasets have been essential to drive C3S in procuring to a very large number of consortia and different initiatives a set of currently 22 ECV datasets. I can mention one, for instance, the one on glaciers, where there is a very important Swiss contribution of the University of Zurich with the World Glaciers Monitoring System, which feeds into provide the data sets that then can be served by C3S in the climate data store. So the plan is to continue building on that and expand the list to maybe 35 in the next 4 years or so. Another story I can tell is the contribution that we are developing together with WMO to contribute to the World Health Organization so-called global burden of disease, which aims to estimate the number of premature deaths due to inappropriate air pollution across the world. That's the source from where you've probably heard that there is an estimate today of about 7 million premature deaths per year. In order to do this estimate, there is a need for having a global picture of fine particulate matter concentration, PM2.5. It's an essential input to this process, but also it's very important in the UN framework because it's also one of the Sustainable Development Goal indicators. The issue before this collaboration started was that WHO didn't have a very good access to, I would say, reliable air quality data with lots of patchy data and sometimes some procedures for processing the data that were fairly questionable in terms of atmospheric composition. So thanks to this collaboration and also with the University of Exeter in the UK, we've been able to collaborate to bring, I think, a much better global PM2.5 estimate that then feeds into this this process and really positioning the contribution of GAW in this realm in a much more visible way than it was in the past. So let me focus for a little bit on C3S. You have the URL here. So C3S has a mandate to convert observations, be it from satellite, from in situ or ground-based remote sensing, into data sets and information product for the benefit of a range of users, public and commercial. And in the middle, there is the so-called climate data store that makes this possible by brokering access to a number of these data sets. So these data sets cover global and regional reanalysis. I will mention a little bit more about that. The seasonal forecast, for instance, the essential climate variable data sets that I already mentioned, access to climate projections, and also support to sectoral applications in a number of domains like energy or tourism, for instance. A visible output of C3S in the last 3 years has been the publication in March or April of the so-called European State of the Climate. It's an exercise that resembles a bit the one of WMO, but at the scale of Europe and building on the different information products that C3S or other services like CAMS deliver to give a snapshot of how the some of the key essential climate variables have changed in the last 12 months. And it's an opportunity to reach to the press and media community and the public about the need for climate action. The biggest success maybe of C3S in the past 5 years or so has been the launch, the development and the launch of the Climate Data Store, CDS. As you can see with this recent snapshot, the number of users is reaching 100,000, which is enormous, given it's not something intended for the general public. It's about, on average, 75 terabytes of data per day, which is downloaded, which is really staggering. And it's really a global success. You see here that many or most countries in the world are using and downloading data. And you can see even that Switzerland is among the countries very active, or that was very active when I took this snapshot, using data from the Climate Data Store. The by far headline product is ERA5, the global reanalysis, and many of the products actually build up the bulk of the data sets and that are downloaded on a daily basis. As part of the next phase of Copernicus, we have at ECMWF a very substantial plan to develop a new reanalysis. So ERA5 is now the gold standard, I would say, and colleagues in C3S are working very hard to develop what will be ERA6, which will be coupling atmosphere and ocean data assimilation. We expect to get several benefits from this coupling, And production of ERA 6 is expected to start by the beginning of 2024. And data probably will be available after a year or two before it can be completed in 2028. So very ambitious plans in terms of new reanalysis, global but also regional, which Copernicus as a program enables, for instance, ECFWF with the funding of our member states would never have had the capacity to have such ambitious plans and to have frequent updates of the global reanalysis. Another aspect which is very important in C3S is the multi-system seasonal forecasts. Currently, 8 systems from Europe, but also from outside Europe, joined forces to produce ensemble products, and Australia is actually joining in the near future. These seasonal forecasts are updated on a monthly basis, and new products keep being added, like this one. It's ENSO index seasonal probability prediction, which we've put online on the CDS pretty recently before the summer. And also, if you go to the CAMS, to the C3S website and the CDS, you can see applications, what we call sectoral information services, supporting a number of activity areas like, for instance, agriculture. Moving now to CAMS. So CAMS covers most aspects of atmospheric composition. It goes from past, current, and near future global and European atmospheric composition and air quality, the ozone layer, emissions and surface fluxes of key pollutants and greenhouse gases from bottom-up and top-down inverse modeling, products in the area of solar radiation, and products estimating climate radiative forcing, that is the changes due to changes in atmospheric composition. And actually, this is the first example that I will take. The Working Group 1 of IPCC has recently delivered its report on the physical science basis. And in this report, we've been very pleased to see a number of CAMS products being taken up, in particular these climate forcings, which was a big piece of work that we've been doing. For estimating these climate forcing, what we've done is to use the CAMS reanalysis of atmospheric composition and greenhouse gases, which spans the period since 2003 to describe the present state. And we've done in parallel some dedicated pre-industrial runs to estimate the pre-industrial state. And from that, colleagues led by the University of Reading in the UK estimated changes in this radiative forcing. And the not so good news is that over the last 15 or 16 years, the net radiative forcings to climate has been deteriorating. So we are not neutral, we are not progressing towards reducing the forcing on climate. We have been unfortunately progressing, so really stressing the need for climate action. Another aspect which has improved gradually throughout the previous period of 7 years in CAMS has been improvement in the skill of the forecast and the prediction capability, and the uptake of these prediction in press and media. In particular, now CAMS forecasts are used when there are very substantial events, and this is an example of a very large dust plume that has crossed the Atlantic in June 2020. And you can see here how dramatic the effect was on visibility but also air quality in Puerto Rico. And you can also see in the bottom that the forecast of CAMS several days in advance, to 4 or 5 days, was really spot on in terms of timing of the arrival of this air mass filled with sand coming from the Saharan region. This capacity of providing real-time estimates and forecasts of, in that case, wildfires and impact on air quality has also been used a lot during this summer. Unfortunately, again, in the Arctic, particularly in the Sakha Republic in Siberia, where 3 years in a row there have been massive fires developing, but also more usually boreal fires developing in North America. And maybe something more unusual was very important fires that South Europe has experienced, Turkey first, and then Greece, southern Italy, and some parts of North Africa, particularly Algeria. So CAM's monitoring of the active fires, of the emissions of pollutants and greenhouse gases, and the forecasts of the impact on air pollution have been very widely used in European and global media to report about the situation as it developed in July and August, also showing that CAMS was one of the only sources with operational capacity that media, TV, and press could rely on to follow the situation. And it's probably one of the key successes of CAMS to have contributed to bring air quality information more mainstream. Now in many websites or smartphone applications that were previously just weather oriented, to see some air quality being presented as well, and CAMS being a source of choice for the quality, but also the operationality of the information that is provided. So it's responding, actually, it's both probably showing that this information is available, and this interest web companies that develop web and smartphone application, but it's also the success of the public that selectively choose applications or websites because also they have air pollution on top of weather information. And also we've been working with CNN and Euronews and now a growing number of other TV channels to disseminate in the form of bulletin information about air quality all across the world. And the result is that very often when there is something ongoing in terms of fires, in terms of volcanic eruption, in terms of very bad air pollution, that we get asked for interviews and for latest information on the situation on the ground. Another area which I'm very happy and proud to report is the progress on pollen forecasting, and it's I think a big success also to the credit of Météo Suisse to have led within EUMETNET the auto pollen program, which is aiming at doing real-time pollen observations and really changing completely the situation of pollen, which so far data was available with a delay of a few weeks. And in parallel, in CAMS, we have been developing, with the help of the Finnish Met Institute, forecasting capability based on the capability of air quality forecasting with an ensemble of models. And in mid-April, we've been able to compare the two for the first time, and it was quite nice to see a fairly nice consistency between the two. And thanks to this work led in Météo Suisse by Bernard Clos, it's been possible to really show that this evaluation in real time is not only possible, but it opens a way also maybe for data assimilation for the pollen forecast, which will mean even better, more reliable forecast in the future. I will go very quickly on the work we've been doing on the COVID. And on the COVID, what I want to report is basically when you look at satellite observations. So that's an average of tropospheric NO2, which is one pollutant, for the period 15 March to 30 April, comparing the year 2020 with the year 2019. And the satellite is called TROPOMI, Sentinel-5 precursor. which is also from the Copernicus program. What you see here is that 2020 was less polluted than 2019 for the same period of the year, but you shouldn't conclude immediately that it is only the result of the lockdown measures that were very drastic at that time in most countries and that were taken. Because if you look at the period 1st of February to 15th of March, just before, you see a very similar picture with less pollution in 2020 than in 2019. While there was no lockdown measures or just a few ones in the north of Italy. So what happens is the role of meteorology. What we could show is that meteorology was fairly standard, was not very different between 2019 and 2020 from mid-March to end April. By contrast, the month of February was really exceptional in 2020. So in 2020, the wind speed was much higher. The planetary boundary height was much higher as well than in 2019. And as a result, not because of lockdown measures, but because of meteorological parameters, the change on air pollution, as can be seen by a satellite, was of the same order. So it's really essential to estimate lockdown, the effect of lockdown from observations, taking into account the effects of meteorology as well. Otherwise, you may say things that are completely wrong. We've continued to work on that topic, of course, not only looking at satellite observations, working with the Barcelona Supercomputing Center. We've developed data sets, bottom-up data sets of emissions of pollutants and greenhouse gases, starting from activity level indicators like traffic counts, energy exchanges. And from these, feeding these into CAMS regional air quality models led by INERIS in France, we've been able to assess the difference properly due to the lockdown measures. And it was nice to see that these estimates coincided quite well with the satellite one once the effects of meteorology had been offset. But what I want to say for the final part of my talk is that air pollution, atmospheric composition is not only interesting per se, it's also interesting for numerical weather prediction. This is an example of the diagnostic of the effect of very large plumes from wildfires. Last year, there were very big fires, as you will remember, in California and a number of states in the west of the US. And in ECMWF system and in CAMS configuration in particular, we could see that these plumes of aerosol had an effect on surface temperature that was up to 2 or 3 degrees. So improving forecast skill really needs aerosol information. And I was super pleased this weekend, literally, to see another example of that coming from the Met Service of Israel in the context of the Southeast European multi-hazard early warning advisory system. And all the more important to report that Switzerland is offering some computing capacity for this effort. And in this work, what has been done by Ariel Muscatel at the Israeli Met Service was to see the potential benefit of using CAMS aerosol forecast in the ICON system run in Israel. And what is very nice, and compare with other configurations that are using climatologies. And what is really nice is to see that using the CAMS forecast, he manages to improve the bias and the RMSC on a period which is a selection of 28 days in 2020, which were marked with high aerosol concentration. So the benefit of using aerosol information, in that case from CAMS, is not only for the CAMS or the ECMWF system, but can be taken up by limited area model by using the daily aerosol information that we provide from CAMS. To finish, I will mention the new frontier or the key new mandate for Copernicus and CAMS within the European Union. It was written in the letter that Ursula von der Leyen sent to the Commissioner Thierry Breton. to use Copernicus for helping with the European Green Deal and helping European countries to contribute to the Paris Agreement and monitor CO2 and anthropogenic emissions. The vision is to develop a CO2 emission monitoring and verification support capacity, which is developed on a model which is very similar to numerical weather prediction or to the way that we've been operating CAMS for now more than a decade, using observations from satellites, from in situ, ground-based remote sensing, using a priori information from modeling, but also, as we've been doing in the case of the COVID, from activity level indicators, and using inverse modeling technique, develop some products about gridded emissions, but also with more refinement over certain hotspots, information about these emissions, and make these emissions available to the governments and policymakers who have the responsibility to discuss and continue the discussion within the COP process, but also the scientific community, the public, and the industry that will help develop new services that will support reducing emissions of CO2. So this is this slide is very busy. It's our roadmap for implementing the CO2 monitoring and verification support capacity. As you can see, it started already quite some time ago in 2015 with a set of reports about how to develop that using satellite modeling and in situ capacity that had to build up. This work has been starting in the context of a number of research projects in which actually EMPA is playing a key role, and Dominique Brunner, who is the leader on this for EMPA, will present with more detail these research effort and the challenges that have been solved and the challenges that are still ahead to deliver such a type of information. At the level of CAMS, it's within our responsibility to build on these research activities to ramp up operations for such a service. Importantly, within Copernicus, ESA and EUMETSAT will have to launch and operate a new constellation of satellites, which are called the CO2M Sentinels, and which will add an observation capacity to the one already available or to the one that other countries in the world, like China or the US, will contribute to the global observing system of CO2. And for CAMS, our mandate will be to start up operation of this service towards 2026. So that it can serve in particular the European member state, but all the countries in the world for the second global stocktake exercise that will take place in 2028. Thank you for your attention. This presentation was very timely. Our Copernicus 2.0 phase is just starting. I would say let's continue to work together with GAW and GCOS, as was the case in the past, and with a number of Swiss entities. And maybe I think there is a large scope for expanding even the collaboration. So I'm very open to answer your questions and to continue discussing offline. Thank you very much.
For this impressive overview on services that come out of Copernicus. We have a couple of questions. I don't know, are you online with us now?
Yes, good morning.
Oh, excellent, it works. That's very good. So Jörg Clausen, Meteo Swiss, asks, for what regions and for what observables do you see the largest need for in situ observation to further improve the CAMS services on climate and health?
Right, it's a very good question, and no surprise coming from York. I think there are a number of blind spots which are also hotspots for air pollution. I will mention in particular Africa, and thinking only at the question of the global burden of disease, it's actually in the areas of the world where the impacts are largest that we lack surface observation the most. So I think it's out of scope to think having a coverage in Africa similar to China or Europe or the US, but having high quality observations like the one that GAW can organize enough to cover Africa. There are also other parts of the world, but Africa is really the biggest blind spot. Would help a lot, and we make sure that all what we can do with satellite and modeling, which has lots of skills but remains as some limitation, it would bring assurance that then this data, when used, for instance, by WHO, gives a proper view of the situation at the global scale.
Okay, thank you. Sonia Seneviratne, she says that she finds the new project between WMO, Copernicus and WHO on the number of premature deaths as a result of pollution very useful, and asks, are there any plans to expand these analyses to the number of premature deaths as a result of climate extremes, which can be attributed to human influence on climate?
I think there are things that can be reused, in particular the value of what WHO and groups working for them, like in that case, University of Exeter, is in the area of downscaling information. So there are things that can be reused. Other things maybe would require specific methodologies. I think what's most important is to work across organization and across specialty areas. So this workshop is very fitting in the sense that WHO are specialists of health. They are not specialists of atmospheric composition. And for a long time, they've been using really low quality information because that's what they had, while through WMO, there could be better methodologies on these topics. And there are other topics where other institutions may bring the best possible expertise. And in order to bring to the negotiation table on the UNFCCC the best possible figures, this across silo approach is extremely important.
Excellent. Jörg Clausen again. What is the relationship between ECMWF CO2 service and where do you see IGIS is still needed?
Well, it's a bit like CAMS and GAW. ECMWF, or it's not ECMWF actually, it's the European Commission CO2 monitoring verification support capacity. I see that as a component to basically deliver the implementation plan of IGIS. So it's a contribution. The number of actors that are involved in IGIS and have been discussing IGIS have made their way into our roadmap that the Commission has now endorsed. So it's I would say it's a symbiosis, and I think we are very fortunate with the ambition of the European Commission to be able to launch additional satellite capacity, which we expect will not do everything, but will bring additional coverage for which currently the space-based global observing system is not enough. And also it has stimulated lots of research, and this afternoon Dominique will speak about this, that maybe without this intention from the European Commission at the highest level would not have happened as fast.
Mm-hmm. Thanks a lot. Maybe another question from my side that is comes sort of solving all the needs or responding to all the needs that we have for air quality information and forecast, or is there a scope for national air quality modeling? And if so, what would be the main arguments that we should bring to our governments to motivate funding such activities?
No, in CAMS, we deliberately stop at a fairly coarse resolution over the globe. It's also limited by capacity and observations. So the resolution of the global system we have is currently 40 kilometers. Maybe we'll go to 20 kilometers in the next few years, but that's already the limit. For European scale, we run at 10 kilometers, and you immediately see that and this will be our final resolution. We have no plan to go beyond. We have lots of CPU to invest in processing better aerosol, etc. So we could, in principle, go to higher resolution, but we don't want. We prefer to improve the system at 10 kilometers and work with the countries at national level that then can downscale to the 2-3 kilometers or even to the street level where they can deliver this information. And the idea is to have a two-way approach so that information at the local scale can be fed into our European and global systems if there is a special event or the knowledge that exists on emissions. And at the same time, if there is a big fire plume or dust that comes all the way to the country, this comes into the forecast, and there is no need for all the countries in the world to have each a global system. I think we need a few global systems, as we see in NWP, and we need at least a national capacity for high resolution. So not unlike I would say numerical weather prediction.
Thanks a lot, Vincent Henry, for your comments. So there are no more questions. We will have you around, I understand, for the rest of the symposium, and we will have you assess what will be said about possible services coming out of GAW and GCOS along our 3 sessions. So thanks again. And with that, I close the first session, the high-level opening session, and inform you that we reconvene at 13:00 for the carbon cycle session. So lunch break is until 1 o'clock, and we start at 1 o'clock. Thank you very much, and have a good lunch break. Oh, yeah, it's time.
It's there. Good.
Good. So welcome back to the afternoon of the first day, to the carbon cycle session. It's a pleasure for me to welcome back on stage Han Dollmann, Freie Universität of Amsterdam. He has an impressively broad range of expertise in the field of Earth system sciences, which span the important portion of the Earth system cycles we are treating in this symposium. In his capacity of chairman of the GCOS steering committee, he perfectly fits to give us an overview on the main elements of the carbon cycle, along with discussing the contribution of its description and understanding of the Swiss science community. So please, Han, take it away from here.
Thank you very much again for the introduction. What I'll try to do is to explain to you some of the things that are happening in the carbon cycle, and 30 minutes is the time limit. And that means that I have to skip over a lot of things. But I will try to do my best. What I will present is largely based on a review paper that we wrote and submitted to Review of Geophysics. It's one of the 3 review papers from GCOS. Carina von Schuckmann led one, Wouter Dorigo led one on water, and Dave Crisp led one on carbon. It came back with a number of in-depth reviews, let's put it like that. And so we're working on a resubmission to do that, and the co-authors are listed there. Just for those who know me, I will move away from the VU University Amsterdam and become director of the Royal NEOS in Texel, which is the Netherlands Institute for Seed Research, from the 1st of November. That's the other 70% of the land, or the Earth's surface, so it's worth looking at that now. This was an original animation, but it doesn't show in the PDF. And the point I was trying to make is that we are now over more than a century concerned with fossil fuel emissions. The first relation between sort of CO2 and temperature was very much directed towards understanding glacial cycles rather than fossil fuel, but that came into the picture and we're now really looking at fossil fuel. That gives us a picture that is drawn from the global carbon budget, and the arrows here show the perturbations in the carbon cycle. And just to say what are the most important perturbations, of course that's the fossil fuel emission that drives everything, and that's the key thing also that we need to change if we want to stop some of the climate change. But it has impact. It has impacts on the land. It has impacts on the oceans. Oceans are taking up more carbon than they used to do. The land is taking up more carbon than it used to do. But there's also a component of land use change, deforestation, if you put it crudely, that brings in CO2 into the atmosphere and has done so over lots of years. The reason why I like to show this graph is that it's important to realize that when you're doing carbon cycle work, is that we have a very active natural cycle. And on top of that, we put in our fossil fuel emissions. And that makes it sometimes very hard to distinguish between what's happening with the fossil fuel emissions or the carbon that's released from that and the carbon that's just floating in and out naturally of those reservoirs. So that brings a very dynamic element to the carbon cycle. The second thing why it's important is that we are planning severe mitigation measures, and we need also to see whether, first of all, how much we need to mitigate, but the second one is also, do they have an impact on the carbon cycle, the natural part of the carbon cycle as such? Because I'll show later how important some of those is. And we need to simply monitor the reductions. In the words of Ronald Reagan, trust but verify. You just like to know how much the CO2 in the atmosphere is going down, and not just what you get from the bookkeeping accounts that are submitted to the UNFCCC. This is a classic picture of what happens with our fossil fuel emissions. They are on top, given here as a source of carbon, and you see also the land use change component there added. Of course, at a particular point in time, we had more CO2 in the atmosphere from land use change than from fossil fuel emissions, but of course that in the last, I think it's the last 30 years or so, that has been dramatically changed. Those emissions are balanced by sinks in the ocean and the land to the extent that only, I think it's 46%, ends up in the atmosphere. So there's a huge reduction because of the activity of the ocean and the land in reducing the impact of our fossil fuel emissions on the atmosphere. And the key thing for the carbon cycle is to see where that's going. Is that continuing or is that decreasing? The way you can see that is if you look at the airborne fraction, and the airborne fraction is defined as the ratio of the fossil fuel emissions and the land use change, or the human emissions, over the natural ones. And you see here that that fossil fraction, the airborne fraction, has remained remarkably close. So this is the amount that, the percentage that still gets into the atmosphere. And that means that the ocean and the land work harder. They work harder every year to counter the fossil fuel emissions. The big question out in the carbon cycle is, will this change? And the big question is, when will it change and how will it change? And to be able to understand that, you need to know more about the specifics of the carbon cycle on the land and the ocean. One of the things that is very important is the feedbacks that might occur. The classic one is the permafrost feedback. If it gets warmer, there's more thaw. If there is more thaw, you have a deeper layer of carbon exposed into the atmosphere that can either be turned into CO2, respired into CO2, or anoxically respired into methane. And that would further the warming. The good news is that we don't expect this to happen in the next 20 or 30 years or so, but there are other things happening in the land, particularly, that might happen in the next 20 or 30 years that have a similar impact on the carbon cycle and accelerate effectively the warming that we already see. So this is an important science question: when and how, which carbon feedbacks kick into the system, and when do they do that? And you can see that in the latest IPCC report, there was depending on the scenario that you take, the fraction that remains in the atmosphere increases. So that means you effectively get more heating. So with the lower ones, we're a little bit at the current situation with 46%. But when you go to the larger ones, you find that there's almost 60% of the carbon going into the atmosphere. The numbers that you see there are the ones that are going into the ocean and the land, so not the ones that end up in the atmosphere. That's 100% minus those. So it's important to realize the importance of these feedbacks. And from a climate observation perspective, of course, do we take the right measurements that allow us to determine whether this atmospheric fraction is changing, and do we have the means to be able to detect whether these things, in terms of the sinks of the ocean and the land, are changing so dramatically that we are on a trajectory where we don't really want to go to. So a few things about the ocean carbon cycle. This is primarily work of Toste Tanua and Judith Hauk and Galen McKinley in the paper. The ocean carbon cycle is in a way very seasonal. It's driven by the gradient in CO2 concentrations between the atmosphere and the upper ocean. And one of the key things in the ocean is how is the carbon transported to deeper layers. And because the turnover times of the ocean are long, certainly compared to the atmosphere, more like in the order of a few thousand years, it's a critical question how much storage you can actually put up in the ocean before it comes out again. How much carbon gets into the ocean? I think the top graph here is the CO2 concentrations. These are taken from a number of stations and ships going around. They're collected in a program called SOCATS, and that now has a huge amount of different data available that allow you to produce these maps. If you convert that into a flux, you basically take the atmospheric concentration and a transfer gradient, and that's probably one of the reasons why you see a great similarity between the top graph and the lower one here. We don't measure the flux. The flux is an inferred value from the PCO2 measurements that are taken. That's an important thing to realize. And the tropical oceans are outgassing, and the higher latitude oceans are taking up. That's a picture you see in the longer term developing in this particular graph. And this graph has a number of models and observations. Observation-based products are these days, to a large extent, also lined up with machine learning techniques and neural networks. We have hindcast models, and there is, in the red line here, is a simple box model. The point I'd like to make here is that we see the ocean increasing still its sink capacity, and there is relatively large variability also noticeable, and this is from 1960 to 2020, so it's more decadal type variability than interannual variability. It's a main difference between the ocean and the land. There's a very large interannual variability on the land. I'll show that in a minute. In the ocean, that's less. If you look just at the box model here, the box model is a model that uses two variables. It uses the concentration gradient in CO2, and it uses the sea surface temperature. And the sea surface temperature is linked up with volcanic eruptions. So it's a combination of those two things that basically generates this red line. And you see that it's working very well, which tends to suggest that at this point in time, it's really still the concentration gradient that's driving the sink. That also immediately puts the question, if the concentration gradient would in any case reduce, because for instance, we are mitigating climate change so successfully, that means that the sink strength of the ocean will go down. So we can't simply count on the fact that this ocean sink will continue in the future. It will change in response to our mitigation measures, and we need to understand exactly how that's going to happen. This is a graph that shows you how much carbon eventually remains in the ocean, and you see that most of it is stored either in the Southern Ocean or in the Atlantic. And the way that's being calculated is using traces to a large extent, and a big database called GLODAPS. Those two databases and the measurements are really critical to the success of these things. And one of the analysis also of the previous graph tended to show that in principle we have very good measures these days with machine learning techniques to determine the uncertainty in these data sets, but we still lack in particular areas of the world, very much like we do on the climate that we discussed this morning, observations that allow us to fill in the gaps. So there are areas with large uncertainty, and we're very good at quantifying those, but we still don't have the observations, even though we now have systems like ARGO running, and we have ARGO biogeochemistry, so ARGO BGC, which is providing really critical data to the deep sea components of carbon. Let's go to the land. Compared to the ocean, and that was one of the things that I learned writing this overall review paper with ocean and land people, the land is a mess. It's a mess primarily because humans have converted so much land, and there's a lot of managed land, which we don't really know how it works very well. We have converted land, so we are left with a history of a particular land use in the soil, and are planting new things on that. And there's also elements like harvest that are taking place in woods that we also need to take into account. So it's much more complex in a way than the ocean carbon cycle. The nice thing is it's a little bit more accessible than the ocean carbon cycle, because you need to go out on ships in the ocean, and you can, in principle, drive on the land, but it's much more complicated. I won't go into detail. What I said earlier about the variability in the ocean, this is a graph that comes from the Trendy network, and it was provided by Stephen Sitch, University of Exeter. And what you see here is the flux, and the flux in the northern hemisphere, the tropical areas, and the southern hemisphere. Two things to note: we don't really have much land in the southern hemisphere, so you can safely ignore the bottom part of that graph. But if you go towards the north of the hemisphere, or the northern lands effectively, you see that there is some variability, but it's on average slightly increasing. If you look at the tropical component, there's very large variability. So the key message from this graph is that most of the variability that we see also in the atmosphere is driven by the activity of the tropical land area. So it's the tropical land area that really is important here. And there are two factors that are important in the tropical land area. One is land use change. We still chop down quite large amounts of forests, particularly in the Amazon, but also large amounts of fires. Those two interact, of course. And there is the effect of carbon fertilization. Increasing concentrations of carbon in the atmosphere essentially make photosynthesis run harder. That has implications to the amount of carbon that's initially taken up. That's the first big flux that we have, but we don't know exactly how that works. We don't know whether that's really going on or whether that's limited by droughts, so we need to have soil moisture observations to be able to do that. We don't really know whether that's nitrogen that does that, although we do have maps of nitrogen deposition. So there's a big debate about that balance between carbon fertilization and, in the tropics, for instance, land use change. In the northern hemisphere, it's likely to be more carbon fertilization. That's something that you see here, not known in the next graph after this one. And the carbon fertilization, similar to what I said earlier about the ocean, it seems to go down, because the increasing amount of carbon that is there and the increasing climate change also counters those effects. And in the tropics, that may be balanced by increased rates of mortality, of which we have a reasonable idea if you look just at the site observations of biomass, but we don't really know how well that's going. And in the northern hemisphere, we think that really is a factor that's contributing to currently increased growth. That's what you can see here in this graph on the right-hand side. You see the northern land gains, not directly measured, but in terms of satellite observations, so NDVI and LEI, gives you an impression how important those are. And there are also some newer ones like VOD, which is a microwave product that allows you to determine biomass, and SIF, which is solar-induced fluorescence, which is directly linked to photosynthesis. And that's also something that you can get from satellites. In the left-hand graph, you see the tropics, and you see the African tropics seem to be relatively stable, whereas the Amazon forest seems to be going down in terms of its total biomass. That's largely due to droughts and increased mortality that takes place in there. This is not just a land use change effect, it's something that's really happening in the ecosystem. From that perspective, you would like to have flux observations directly over those elements, and we only have a few flux stations, for instance, in the Amazon. The problem with some of these elements that are playing a real critical element in the carbon cycle is that those are particularly the areas where we don't have the observations. We don't really have many flux observations. We don't really have many CO2 concentration observations. And there was a paper by Luciana Gatti, I think just a few weeks ago, where they took the observations with aircraft, but you'd really like to have long-term sustainable observations going there. All of that was funded by short-term research funding. And they basically showed the same picture, that the sink in the Amazon was going down. I'll skip this for time. This is a graph that we produced for this review, and it shows the relative errors in the annual budgets that are coming out from the GPP. And so what it shows is that most of the errors remain remarkably stable. We haven't really been able to reduce the errors very much, and the errors in the total budget are really dominated by the land sink and the land use change component. Those two elements in the land determine our capability of the land to determine the global carbon project. And that's really critical in the sense that we think we have enough observations from satellites to produce land use change, but we don't really know exactly how well they're not repeated consistently enough to be able to determine the change properly. And that's really where additional effort needs to be taken into place, next to, for instance, improving observations in the oceans and the others. That brings me to the status report of GCOS. I think in principle we need to thank Oksana and GAW for putting up a really efficient and well designed system to measure all these the different trace gases, and in particular CO2, but they do still suffer from inhomogeneous distribution around the globe. That has not so much maybe impact on determining the global average CO2 concentration, but it has phenomenal impacts on our ability to determine the regional sinks that we're increasingly trying to produce. We have a number of satellite greenhouse gas observations. There are satellites out there, GOSAT, OCO2, and Vincent Henry already mentioned CO2M. That's being planned. They're not necessarily at the moment very well sampled with CO2M. That's likely to change, and that's likely to be a real step change in our capability. But at the moment, that's not the case yet. The biomass maps on which some of those graphs of the Amazon that I showed you were produced have little consistency in assessing that change. And really, we can't determine from satellites the high biomass values because the satellite signal basically saturates when you have too much biomass. Burned area, which is a key product on land use change, it's the first step when you're trying to determine the emissions from land use change. There are still large omissions in the data that we have. And as I mentioned, land use change reporting is still a big issue. And it's not done regularly, and it's not specifically done for the purpose of carbon accounting. If you look at the ocean, we know how to measure it to some extent, but there are still gaps, and there's a large range in the quality of some of the data. And the really big thing is, of course, that in the Northern Hemisphere, our knowledge is reasonably well, but in the Southern Hemisphere, where most of the things are happening with the carbon cycle, we have far less of observations. Chlorophyll, which is the key thing with the biomass, or the biotic pump, is generally quite good. But if you start comparing some of the products from satellites, there are very big differences. Oxygen is also available, but there's again, a large range in the adequacy of the data. And again, it's better, we have better coverage in the northern oceans than in the southern ones. And when we start talking about really the biotic aspects of the ocean, mangrove, seagrass, that's very incomplete in terms of sampling. So there's a lot to increase just our perspective of the global carbon cycle. Now, and I think we have some of these talks later on, and Vincent Henry also mentioned this, there is a big push for budgeting and monitoring system to basically determine compliance to climate agreements. And I'm very much in favor of that. But it does pose a number of questions for GCOS. The timeline, as you see here, I think Vincent Henry showed the same graph. In 2025, so in 4 years' time, the system has to be operational. So there has to be at least one satellite flying for Copernicus CO2M that does this. So there's an enormous concentration of effort to get this right in the right time. And to be honest, we're not there yet. We're not there yet at all. And so the next 4 years, we'll see whether, with a number of projects, we can actually achieve this, but that's going to be tough. And there's an awful lot of data needed for this thing. And if you look, for instance, at the observations, which would be the area where you think that's likely to be GCOS, you find that the type of observations that are being needed and the frequency of those observations and the spatial domain of those observations is sometimes fundamentally different from what you would do if you were just interested in the continental scale or the global carbon cycle. And that poses questions, and it's particularly CEOS, the satellite agency, that's also pushing GCOS to make a distinction into the application areas for which we use some of those satellites. And that's a discussion that we have to take place when we start preparing for the next implementation plan. We have some new observations. We can do now global biomass. We have new machine learning techniques. This is one where we use FluxNet and compare it with Trendy. You see the pretty large difference, by the way, what our models predict and what you observe by flux towers. And one of the key things that came out of the COVID is that we have these real-time, almost real-time monitoring techniques, something that Sonia mentioned earlier, where we can see what's happening, particularly in the transport area. This is still proxies, so there is very large uncertainty with this. It looks all very nice, but some of the people who are really experts in fossil fuel tell me that the errors involved here easily run up to about 50%. But it is something that policymakers are also increasingly interested in, because it gives them a real-time view of what is the human impact on the carbon cycle. And of course, that's something that you would really like to know. So we need to deal with those things. And of course, the overall big question that relates also to this cycle is what we currently have in terms of GCOS. Is that adequate to tackle those issues, both on the science side and the budgeting side? So this is my final slide. I have 4 big questions. One of them is that traditionally within GCOS, we go for the state variables, which means we try to observe biomass. But that's not enough. We need to know the fluxes, as I've shown on the ocean and land. It's the fluxes that are the real things that are interested. So how do we do that? Should we specify specific requirements for applications? So like, if you want to use this budgeting at a specific scale, do you have a different requirement for your satellite or your inversion that you would like to use? How to incorporate some of these new techniques, artificial learning, etc. And this is a point I try to make every time, how to balance the in situ needs and the coverage of the in situ need against the satellite. There are a lot of people out there that think that satellites answer everything, and that's simply not the case. We always need to combine the in situ observations, and when they are sparse, we need to put in significant efforts to upgrade them against the satellites that have, by definition, global coverage. Thank you.
Thank you very much, Han, for this presentation that seemed jam-packed with knowledge and concepts to me. I have a few questions coming in from the audience. Let's start with a fairly easy one to understand. So Marco Arpagaus of Meteo Swiss asks, why is the carbon uptake so different between the Atlantic and the Pacific Ocean?
It has to do with the temperature of the ocean waters. Cold water can hold more carbon, more CO2 than warmer water, so it tends to outgas in the tropical areas.
Okay. Then we have, are there estimates how much changes in the ocean circulation, like weakening of the Gulf Stream, will affect the CO2 uptake capacity of the oceans? Will it matter globally? So, question.
That's a very good question. And I don't have a direct answer. The changes in the ocean circulation and the overturning take place on longer time scales than the ones that we have seen so far in terms of the uptake. So the expectation is that will not be, certainly not be an immediate issue, but in the 50 to 100 years from now, that could take place. But as I said, I'm not an ocean expert, an ocean circulation expert, and for the time being, what we say in the paper is at least that this whole system of increasing concentration gradients will probably reduce, but once there is such an overturning, it will dramatically change the picture, but we're not there yet.
Another question: in the past, the land uptake was computed as residual of all other components. How consistent are today's land biosphere models with this residual? And can we sufficiently trust them to make good prediction for future carbon uptake by the biosphere?
I think it's in the certainly in the last global carbon budget, there is no land uptake that was counted as a residual anymore. That was in the previous one, it was done like that. But now we run the DGVMs, the vegetation models, to produce the carbon uptake and also give an estimate of the land use change. And so what you end up with is a total residual. And I think you could, if I go back very quickly, so, no, that doesn't work because it's one of the first graphs. If you sum up the sinks and the sources, there's a little bit missing. And that's the current residual. And I think that's 0.2 gigatons a year on average. So that's to, yeah, this one here. It says, yeah, it's in white, but it effectively tells you how well the sources and the sinks match. And as I mentioned, we now determine each of these sinks independently. So the atmosphere is measured by the mostly by the in situ observations. From GAW, that we have the land sink that's determined by models, and we have the ocean sink that's also determined by oceans and by models and by observations. And so we have these independent estimates. Then you're left with one single residual, but that's the residual of the overall carbon cycle, not the land part anymore. Okay. That was changed, I think, last year in the global carbon budget.
I have a last question regarding the simple box model for carbon uptake. The question says, I suppose that the two box models used average concentration, gradient, and fluxes. How can this describe so well the complex reality calculated by Earth system models?
I don't know. I think it's an ocean question.
It doesn't say the name, so I
don't. I think what it does is it takes the key elements of the global carbon cycle, and apparently the variability of those elements is very much driven by those two variables that the box model is using. And I personally like these very simple models, in a sense, because I think they tell you a lot more about what's really important than our enormously big, complicated models, where it's always very hard to tease out what is exactly doing this. So if you have a simple model that does get the right interannual variability compared to the observations of some of the other models, I think you have a pretty good chance that you are beginning to understand exactly what's happening there. Mm-hmm. So I would turn that question around a little bit, as I said.
So maybe the person who posed the question will approach you in the coffee break.
Yes.
So I think.
And I'm not an ocean modeler.
I think we should move on to the next speaker in the session, Michelle.
Yes, exactly. So after this keynote address, we advance in the program with our first national speaker of this afternoon session. It is my pleasure now to introduce Benjamin Stocker. He is professor at ETH Zurich at the Department of Environmental Systems Science and the head of the group for computational ecosystem science. His presentation is titled From Weather to Ecosystem Forecasts, Opportunities for Reliable Carbon Cycle and Climate Impact Projections. Unfortunately, Benjamin cannot be with us here at Centrum Paul Klee and has recorded his talk, but he will be available for your questions afterwards. So please, Technic team.
Good afternoon. Thank you very much for giving me this opportunity to present here today in the form of a video. However, I'm also live present now in the Zoom session, and I will be with you in Bern tomorrow on Tuesday physically. So I'm going to share my screen to get started. All right. So as climate change is altering Earth system in very different ways, the terrestrial biosphere has moved into the focus. And this is because terrestrial ecosystems are currently absorbing about 1/4 of annual anthropogenic CO2 emissions. And the vegetation mediates surface atmosphere coupling and thus the very strong water vapor climate feedback. And third, climate change effects are particularly expressed through impacts on species and ecosystems, both natural and agricultural ecosystems. And we need to know sensitivities and threshold of impact, and we need to develop capacity to forecast such impacts of climate extremes. So in this presentation, I'm trying to outline how we can best design research and infrastructure to better understand the third point here. So overall, the aim is that we should extend the focus from weather to ecosystem forecasts and provide near-term forecasts of climate impacts on multiple variables and across space. So the task is basically to account for the weather in preceding months, maybe years, and to provide forecasts at the level of weeks to months, or in other words, accounting for medium-range weather forecasts and provide so-called near-term ecosystem forecasts. And we want to do so across space at the scale of Switzerland, at least, by accounting for effects of topography, soils, land cover, etc. And to do so, to generate impact forecasts, we need to understand the state and the response of the vegetation to the environment and its variations across space and between days. So that means that we have to learn from past observations. So let me give you a few examples to make just this case that we need to understand vegetation to forecast impacts. So one example is the advancement of spring phenology. What you see here is a time series of so-called spring index, which is based on phenology observations in Switzerland. And you see an advancement of the spring leaf out to earlier days over the course of the past several decades. However, the advancement of the spring leaf out is not paralleled with an equally rapid advancement of the late frost events. And what this means that vegetation tends to become more exposed to such late frost events, and that what's happened a few years ago. This is now a picture taken on such damaged trees affected by a late frost event that happened in Switzerland. Another example is that the fact that the earlier spring green up also means that cumulative transpiration during spring months is enhanced. And this can, of course, have effect on the water stored across the plant's rooting zone as it gets earlier depleted and thus predisposes the vegetation to be under a higher drought risk in the summer months. And this has indeed been observed and impressively documented for the year 2012 across the US Midwest here. What these plots here basically show are the relative anomalies in FA par, and this is a measure of the vegetation greenness, and it essentially quantifies the fraction of absorbed photosynthetically active radiation. Now, to understand carbon cycle impacts of such droughts, we need to understand not only the vegetation structure and how it responds to environmental change or climatic events, as quantified before by the FA par, but we also need to understand how photosynthesis responds. Now, photosynthesis at the level of ecosystem, here quantified or defined as the gross primary productivity, is determined not only by the structural components, but also by leaf physiology. And specifically, we can express this as the product of radiation, the fraction of absorbed photosynthetically active radiation, and the so-called light use efficiency. Now, the challenge is that light use efficiency is hard to observe from space, but we can learn from local flux measurements. And that's basically what we did here. And we found that not at all sites responded the same way. At some sites, the light use efficiency was strongly reduced when the topsoil dried out. And that's what's shown in the top panel here. However, at other sites, we found almost no influence by soil moisture, and plants seem to be very active in spite of the topsoil being completely dry. Now, this is indicative of a spatial heterogeneity of such responses to drought. So some of these sites that behaved like the one below were located actually on riverbanks where the groundwater table is relatively shallow and where tree roots might even access deep water stores. So you see that for predicting impacts, we need to account for the preconditioning and the temporal dependencies. So think, for example, of the phenology drought example that I showed. And we also need to understand the spatial heterogeneity of responses. Finally, and this I haven't shown any example here, is that we need to deal with both impacts of individual meteorological events, but also of gradual environmental change. Of course, there's a lot of data that we can learn from. Particularly in Switzerland, we can benefit from established networks of ecosystem monitoring. So what this shows here is the Swiss FluxNet that is maintained by colleagues at the ETH. This is essentially a network of covariance flux measurements that provide continuous observations of ecosystem atmosphere exchange fluxes of CO2 and water vapor. And some of these sites are also integrated into European and global networks. To be mentioned is the ICOS, the Carbon Observation Network of Europe. There are also other networks of forest monitoring. What I'm showing here is an example, the long-term forest ecosystem research, the LWF, indicated here by the blue dots across Switzerland, where in continuous fashion, several variables are measured in parallel, including meteorological variables, phenology, soil moisture, soil matrix potential, etc. And also these sites are integrated within the so-called ICP Forest and LTER Europe. So these are international networks with similar measurement protocols. Other networks, for example, the TreeNet measures continuous stem growth. Sana Silva measures tree damage and mortality events. And there are even some experimental sites in Switzerland where ecosystems are perturbed, and we can learn from these. Now, at some sites, the Swiss FluxNet intersects with some of these other networks, and a multitude of variables are measured in parallel, actually. So two of such super sites are Davos and Legen here in Switzerland. And this illustration here shows the wealth of different types of measurements that are available at such sites. So this includes meteorological variables on the left here, then measurements of water fluxes in a continuous and high frequency fashion, including measurements of tree transpiration. Then we also have measurements of longer term changes, for example, of nitrogen deposition and ensuing effects on the stoichiometry of biomass and nitrogen leaching, but then also forest inventories and tree growth measurements. Now, of course, there are also challenges to work with this data and to learn from this wealth of observations. So, for example, the challenge is the fact that some of these sampling locations are non-congruent. But we do have these super sites. Of course, there are also uneven sampling intervals, which may pose some challenges for certain methods. Then the combination of information from multiple variables is actually a challenging aspect, particularly for machine learning methods, which I'm going to mention just afterwards. And the fact that we know that there exist mechanistic links between multiple variables suggests that we might be missing crucial information to make use of these multiple parallel observations. And of course, stakeholder relevant quantitative information is often missing. And last but not least, the spatially sparse observations paired with the fact that we know about the large spatial heterogeneity in ecosystem and their responses to the environment pose a large challenge. And such spatial heterogeneity is caused by small-scale variations in the soil, for example, effects by landscape position and implications for the hydrology and the microclimate. And this is where a different type of observations comes in, of course, remote sensing. So there are basically two types of remote sensing that are particularly relevant in this context. To be mentioned is the sensing of spectral reflectance in multiple bands, which provides information about mostly greenness structure, but also to some extent physiology, which I'm going to mention afterwards again. The second very important type is thermal infrared remote sensing, which provides key information about the surface energy partitioning and therefore also on plant stress. So taken together, these observations provide information at multiple levels, from site to trees, across the landscape, and even across the scale of Switzerland, across space. Now, how can we integrate these and make forecasts? So that's basically where models come into play. So for ecosystem impacts modeling, there are basically two avenues, both with their advantages and disadvantages. First, there are machine learning approaches, in general data-driven approaches, and second, mechanistic ecosystem models. Let me give you some avenues of machine learning model application in this context here. That's actually two examples from work in my own group, where in the first example here, we are predicting ecosystem growth primary production at the scale of individual days. And so this is also attempting making the forecast, because it's temporally generalizable, the types of models that we're developing. This provides also the ability to forecast impacts given the temporal dependencies, because that's also an aspect that the model can learn. And indeed, this seems to work quite nicely as shown here, which is just a comparison of out of sample cross-validation from a physical model, a mechanistic ecosystem model basically, versus a machine learning approach, which indicates the machine learning approach is actually outcompeting the mechanistic model in most cases. Individual points are sites here. The second example is to show that by applying machine learning methods, we can more effectively make use of the information that is contained by spectral remote sensing. So the spectral remote sensing and the derived vegetation indices, which are widely used, they mostly provide information about the structure, but to understand, for example, how light use efficiency and plant physiology responds to drought stress, we need to go beyond. So we need to effectively extract information from this full spectral information. And indeed, we may be able to do this more effectively as we have in the past, which is just indicated by this graph here at the bottom. Then another area where we're applying machine learning for impact prediction is for understanding or forecasting vegetation browning events. And the approach here is that the suitable algorithms can not only learn temporal dependencies, but also spatial dependencies. And from that, they should be able to learn relationships between climate and its history in preceding months and vegetation greenness, and how this all depends on the landscape position. I cannot show you any results yet because I'm still hoping for funding to get this work started. So, but the data that we have also limits some machine learning applications in some respects. So uneven sampling intervals, for example, are a limitation for most algorithms. Often machine learning target a single variable like greenness or GPP, and often we have observations on multiple measured variables measured in parallel, as I mentioned before. And so effectively making use of this combined information is challenging in general, and somehow we need to account better for the mechanistic links between them. Often the quantity that stakeholders are interested is often not the target variable for machine learning applications. And this is because machine learning methods are data hungry, and variables of interest might not all be measured as frequently as the one that are most relevant for stakeholders. So in this respect, really, mechanistic ecosystems models offer a solution. And this is because they explicitly resolve the links between multiple types of observations and variables. So for example, in this figure that I'm showing here, as time into a rain-free period evolves from the left to the right, first plant stomates close, which later reduces also the photosynthetic capacity, which reduces carbon assimilation and growth, and in a prolonged drought may also reduce the amount of green foliage. And the responses finally lead to an enhanced risk of mortality. So there are these links, and mechanistic models resolve the processes that cause these links. And there are a set of key advances in mechanistic ecosystem models that make these models actually fit for applications in near-term ecosystem forecasting for climate events. So first, explicit representations of plant hydraulics are becoming implemented in models, and this enables various measured plant traits to be used for parameterizing these models, and therefore more realistically simulate species-specific responses to water limitation. The second, which I'm mentioning here, are the cohort dynamics and the height structure within a stand, which are now explicitly simulated by the latest generation of models. And this now enables actually the simulation of sensitivity to water stress as a function of tree height. And also it allows the explicit treatment of the implications of disturbances on forest dynamics and biomass balances. So taken together, this enables models to make use of a much wider variety of data. And finally, data assimilation methods are becoming available and also more user-friendly to implement the effective integration of these multiple types of observations into models. So this enables the integration of these multiple observations that may also be given at multiple observation intervals. And therefore, the models can actually be used as so-called scaffolds to fuse multiple data sources. And this development has also recently been heralded as an ecological forecasting in this paper by Dietz et al. So in the context of ecosystem modeling, such near-term climate impact forecasting, data assimilation actually means the integration of these types of continuous observations made at all the different levels into mechanistic models. And the most widely applied route is the Bayesian model optimization, where basically model parameters and their entire distribution are constrained by the observations to yield a set of parameters that best simulates the system of interest or a specific species. Then, of course, over time, such parameters are constant, but repeated observation prediction evaluation cycles enable repeated model updates and increasingly reliable predictions, and also to identify gradual shifts of the state and structure of ecosystem and shifts in sensitivities. So to wrap up, I argued here that ecosystem forecasts are possible, and that this enables multiple applications. This includes early warning systems to extending the weather forecast to provide stakeholder relevant information about the unfolding climate extremes and their impacts. This is crucial for supporting management decision because the types of models that are available or are becoming available are species-specific models and that are applicable at the stand scale by accounting for topographical effects and the landscape position. And such models then, of course, can also be used for scenario projections and to evaluate alternative management options in climate change scenarios. And we can learn by integrating these types of observations into the modeling, and we can learn from repeated prediction validation and model revision cycles. And finally, this also lets us improve numerical weather prediction. Think of the vegetation-climate interactions. Last but not least, I would also like to argue that we should be moving beyond indices. So after all, impacts are governed very strongly by the state and the response of the vegetation, and we need to be able to provide stakeholder relevant information for making decisions or for guiding decisions. And so with this, I would like to thank you for your attention, and I'm looking forward to answering your questions in Zoom.
Thank you very much, Benjamin. Can you hear us?
Yes, I can.
Very good.
Can you?
So happy to have you here, and thank you very much for your presentation, including the aspects of machine learning and the different applications. I have one question here on my pad, which is, are there ideas to tackle the issue of spatial heterogeneity by dense networks of low-cost sensors, at least for some proxy parameters?
Yeah, I guess the limitation or the challenge here is to have low-cost sensors on the relevant quantities. we learn very much from these ecosystem flux measurements, and they are not low cost. So these are these eddy covariance towers that have to be maintained over the course of several years or decades, and they're certainly not low cost. And of course, they have a limited representativity, a spatial footprint of on the order of a kilometer. And so this is actually a challenge, because even if we increase the number and enhance the density of these eddy covariance networks, we will never be able to fully cover the landscape. But I guess, like, by the combination of what we can learn from these local measurements and how this relates to what we can sense with satellites, we can actually get at the more spatial coverage of information. So we have to more effectively establish these links between the local observations and what the satellites provide in terms of, for example, response of the physiology to stresses. And I think that is, in my view, a very promising route forward.
Okay, I gathered that Andrea also has a question.
Yes, you talked about data simulation. Data simulation is the first step to forecasting, and you mentioned ecosystem forecasting. And what I'd like to just have a number on is the timescales, and what timescales you suppose this will impact or benefit weather forecasting.
Yeah, I think the timescale here is probably most strongly limited by the reliability of weather forecasts that actually go into, or can be considered as a forcing for the types of ecosystem models that may provide these forecasts in the end. So as I also mentioned, most of the approaches for using data assimilation in combination with ecosystem models, they implement so-called Bayesian parameter optimization, where the parameters are essentially constant in time. So the same model would be applicable at any point in time. And really what's limiting in that respect is just the weather forcing. So I guess the applications here would be most useful at the scale of weeks to maybe months.
Okay.
Bringing it down to a single number, yes.
Yeah.
I have another question here. In the meantime, early warnings extending weather forecasts sounds good, but given that growth times of forests are decades, is most of this not coming too late?
Yes, of course. In some respect, yes. We cannot replant a forest if we see that the weather is developing unfavorably over the course of weeks, of course. However, it's important information to provide locally to adapt management. I mean, this could be direct responses. In Switzerland, may be less relevant at this point, but maybe more so in the future, are of course prevention of wildfires. Then a quantification of impacts is also important to guide like forest management decisions. And of course, as I mentioned, to just be able to learn from such model data, integration is also a way forward to better understand the system and how it would respond to future climate change. So the same systems may also be useful for scenario projections and guiding sort of a longer term forest management decisions, for example.
Okay, thank you very much, Benjamin, and looking forward to meet you here at Zentrum Paul Klee tomorrow.
Tomorrow, yes. Thank you.
I'll hand over to Andrea for the next point.
Okay. Thank you, Michel. Our next speaker is Markus Leuenberger. He's professor at the University of Bern, the Institute of Physics. Among other, he's the director of the high-altitude research stations Jungfrau Joch and Gorner Grat. Indeed, Markus initiated continuous CO2 measurements at the Jungfrau Joch station in the early 2000s. Today he's going to talk about the combined oxygen and carbon dioxide measurement as a tool for the partitioning of carbon dioxide emissions among the carbon pools, atmosphere, biosphere, and ocean. Please, Markus, the floor is yours.
Thank you very much, Andrea. Good afternoon, everybody, remotely or here in the auditorium. Han Dolman already mentioned a key question that interests me also for a long time, and this is indeed to know where the carbon goes that we emit to the atmosphere. And of course, we already have seen that this distributed to the ocean and the biosphere. Andrea already mentioned that I started up a CO2 record in Switzerland at Jungfraujoch, a remote station, and for the concept I would like to talk about, a remote site is important. You can see here on the left-hand side the hourly means of these records, CO2 on top, and you see this increase as documented by these fossil fuel releases to the atmosphere, and on the lower panel you see the decrease of atmospheric oxygen, because these two cycles, the carbon cycle and the oxygen cycle, is very tightly linked. On the right-hand side, you see the monthly means. You get smoother records there, and one can calculate from that then also the long-term trend. And this is given by the numbers of 2.27 ppm per year increase in CO2, and in oxygen a decrease of minus 23.3 per meg per year. This per meg unit has to be converted to directly come up and compare the CO2 change with the O2 change. We can do that by multiplying this number with the oxygen fraction, and that leads then to a number of 4.87 ppm per year for oxygen change. So when we look at the ratio of these changes, we end up with 2 moles of oxygen change per mole of produced CO2, more exactly minus 2.15. The concept now is displayed in this graph. When we plot the oxygen on the y-axis and the CO2 on the x-axis, we can now look at annual means and look at the black dots. From 2005 to 2020, we have these annual means, and these are the observations in the atmosphere. We can compare that what we would expect if all the emitted fossil fuel CO2 would remain in the atmosphere. These are the red squares there. And we end up to a lower value in oxygen and to a higher CO2 value compared to the observation. On the top of these fossil fuel emissions, and the O2 change can be calculated by calculating the fossil fuel emissions times the so-called oxidation factor. We had to up on top of that the land use change, as we already have heard of. That is a contribution to the carbon cycle. And there we have to multiply the CO2 emissions to get to the O2 emissions by the biospheric oxidation ratio. These are different. Here, mean numbers are given. And now, to close the budget, we need to come from one end point of the observation to the end point from these fossil fuel and land use changes. And that can be calculated based on known processes that the ocean is taking up carbon, mainly through carbon chemistry, and the biosphere is also taking up CO2 through the fertilization effect, through photosynthesis, respiration, but photosynthesis in that sense wins, and we have a net gain of the terrestrial biosphere. So the question related to this approach is, of course, how robust are these oxidation ratios? How robust is, for instance, also the set value, the outgassing of O2 due to the thermal or the temperature increase of the ocean water? And what about the temporal changes of carbon distributions among these reservoirs? So to look at the oxidation ratio, we first of all look at the ocean, and there the biosphere is quite balanced, and the ocean acts as a carbon sink, but a slight oxygen source to the atmosphere. Regarding the terrestrial biosphere, we have an oxidation ratio of about minus 1.1 mole O2 per mole CO2. This is related, of course, to the well-known photosynthesis respiration equation as given here, but also we have to remember that we have to oxidize nutrients as well. Therefore, it's slightly deviating from a minus 1.1 line. Fossil fuels, there we have three main sources: natural gas, methane, and to oxidize that we need 2 moles O2 per mole CO2 produced. We have coal with an oxidation number which is significantly lower, minus 1.17, and gasoline with around minus 1.4. So the mixture of these fossil fuels are changing over time. And this is from the Global Carbon Project, a summary. And as you can see here, the coal has increased between 2000 and 2010, mainly through the usage of coal in China. And that led to a significant, a change in the oxidation ratio from about 1.41 to about 1.38. So we have to have that in mind. But also in the lake, of course, we have the biospheric activity, and there we would expect a ratio of about 1 to minus 1.1. But there are many different processes involved, like carbon precipitation or dissolution, especially also in the ocean compared to a lake. And photosynthesis respiration can be measured actually by doing these combined measurements of O2 and CO2. And on the right top panel, you see such plots, and they align very nicely at this one-to-one relationship. Also, when we look at the terrestrial biosphere, we can, for instance, here in this study of Helm, who tested a low-cost setup to measure both O2 and CO2 in combination, here in this testing phase for wheat seedlings. And when you look at these temporal slopes, you see both 1.27 and minus 1.27 as a function of time. And when you take the ratio, you end up again with an oxidation ratio of roughly minus 1 with quite a small error. We also did measurements at Bern and at Beromünster Tower. On the left-hand side, you see on the top panel the temporal evolution of combined CO2 and O2, and when you cross-plot them in the lower panel, you see an extremely nice correlation with an oxidation ratio of minus 1.4. So we clearly can say these are fossil fuel emissions associated to this change. That is in the Bern city. That's acceptable, of course. When we go to the right panels, then we see again now aggregated monthly means displayed on each day hours. You see again this very nice anti-correlation. And on the lower panel, you see the correlation and the oxidation ratios are now close to minus 1 over the whole day. But you see also a small hysteresis effect. When you only look at nighttime or daytime hours separately, you end up with a value for the oxidation ratio of about minus 1.1. So we can come back to this graph here and add uncertainties, and that blurs these calculations, but still there is a mean contribution of the emitted CO2 that goes to the ocean, which amounts to 26%, to the biosphere of 29%, and already mentioned by Han, around 45% resides in the atmosphere. But of course, and the uncertainty are quite acceptable in the order of plus minus 6% for both the ocean and the biosphere, and they are interlinked. So looking more closely to the ocean and where is actually the oxygen dissolved in the ocean, you see on the left upper panel this distribution, and it's more or less evenly distributed. On the lower panel you see the decadal change since 1960, and it corresponds to roughly a few % of change based on the amount of dissolved oxygen. On the right side you see the distribution of this oxygen now split up as dissolved oxygen per latitude, and in red the apparent oxygen utilization. That means when we add these two numbers together, or these two curves, we end up with the saturation oxygen that is expected corresponding to the temperature. You also see as a thin red line on the second upper right panel the effect of the solubility only. So that means you see quite a strong variations of the black and gray range there, and this has mainly to do with the circulation and not only with the thermal solubility changes. That's important to be known. On the lower right graph, we have the vertical distribution of this dissolved and apparent oxygen utilization, and also the change over decades. So to summarize, global global oxygen budget can be looked at as put together by Huang et al. In 2018. We have an atmospheric decrease in oxygen that we can measure, mainly driven by this fossil fuel combustion. However, when we look into cities or where a huge population are present on Earth, we have to consider also human respiration or livestock respiration. And of course also the wildfires that has been mentioned before. The balancing fluxes are the ocean outgassing. However, this is a quite small flux. A larger flux is the land production, producing oxygen, and we have to be clear here. This is a number for the net ecosystem production, meaning the GPP minus the autotrophic, heterotrophic, as well as the minus the microbial decomposition. So when we look at the four main consumption areas or types of O2 changes, then we have the fossil fuel, the human respiration, and the livestock respiration. And when you look at the global distribution, they are very similar because they are linked, of course, to the population distribution. The fire on the right panel below, there we see a different spatial distribution because that has not directly to do, of course, with humankind, except when we think of course, the tropical forest clearing, etc. The temporal evolution under historical changes, plus when we assume now an emission scenario of RCP 8.5, the oxygen budget looks like that. So we have a strong O2 flux increase due to the combustion of fossil fuels. This cannot be balanced actually by the increase of the terrestrial biosphere as given here. And these are huge changes in O2, a decline of around 100 gigatons per year when we follow this track in the year 2100. Interesting is, of course, how actually these changes translate then into changes in the land O2 flux or the ocean O2 flux. And for that, I looked into a publication of Huang again. He actually put together CMIP 5 simulations. Here are the historical values translated into land O2 fluxes and ocean O2 fluxes, and what you can see is, as expected, the land is actually always a source, or was always a source. That means the carbon is stored, additional carbon is stored in the terrestrial biosphere, and in the ocean you have either a flow out from the ocean to the atmosphere or vice versa, and a clear distinction spatially. More important is now how this develops when you look at different scenarios. So in these two graphs here, the difference between RCP 4.5 scenarios minus this historical flux distribution as just shown. On the left-hand side, again, for the land, on the right-hand side for the ocean. And you can clearly see that there are changes on land, mainly in Asia and in Africa. When I go back again, you can see now the changes there in Asia mainly. And the changes then in the ocean is mainly in the equatorial Pacific and in the North Atlantic as seen here. And these changes get even more pronounced when we would follow a track of the RCP 8.5. When I go back to the 4.5 minus historical and then 8.5 minus historical, you can clearly see that. So this graph was already shown by Han Dolman, and this clearly says that there is a limitation also of the ocean and land uptake. It still takes up more if we emit more CO2, but a larger part will remain in the atmosphere. And that directly turns also or has implications on the concept that I just shared with you, namely that this oxidation ratio that is seen and can be measured in the atmosphere will decrease over time if these model calculations are correct. And with that, I come to the conclusions. So combined CO2 and O2 measurements at remote locations are capable to partition this emitted CO2. When we go to rural or urban sites, we are able to actually quantify this oxidation ratio because they, when they are known very precisely, then that directly translates in a lower uncertainty of this partitioning. Critical are this oxidation ratio of the fossil fuels. Therefore, we have to know exactly the mixture of these fossil fuels to be used or which are used, and associated ratios. New techniques are available now, especially we are using a cavity ring down spectrometer that allows very precise and continuous measurements at remote locations with excellent temperature control. And in my view, we should go that way to increase the number of sites where we do parallel measurements of O2 and CO2. Thank you.
So thank you very much, Markus, for your presentation. We have a question from Tom Peter, ETHZ. He says the diurnal variation of CO2 can easily reach 60 ppm in the Swiss Midlands, over the Swiss plateau. Does this not compromise the measurements in Switzerland, since a considerable averaging has to be done?
That is, of course, correct. That's why I really strengthened here that if you would like to do a budgeting, a carbon budgeting, you need to go to a remote location. The air at Jungfraujoch integrates over whole Europe. When you go to a local site like Beromünster, which is actually dominated by biospheric processes, of course, then you can't do this budgeting directly, but you can say something about the oxidation ratio, and you could try to quantify actually these biospheric changes. The fossil fuel contributions can be quantified, and we do that at Beromünster through radiocarbon additional measurements.
Okay. Another question, it doesn't say who did the question, is continuous O2 N2 measurements are very sparse, most likely due to the technical challenges. Is flask sampling and offline analysis sufficient for determining the partitioning?
Well, depending on the frequency of these flask samplings, of course, that has been done in previous times because indeed the oxygen measurement is quite time-consuming and delicate. But now with these new instruments, we are now in a situation that we should go for continuous measurements because we get much more information out of it, and we get a better robustness of the partitioning results.
Excellent, thank you. So maybe questions continue to come in. I heard that there is a fair amount of delay between us and the live stream on YouTube or GatherTown. So I encourage people who are following us online to pose their question rather earlier than just at the end of the talk. Okay, with this I hand over to Michelle for...
And I keep it very short since we have foreseen a short break now. We are a bit behind our schedule, so we propose to reconvene here in the main conference hall at 2:30 in a few minutes' time, just a short break.
Next speaker in this session will now give his views on possible and desirable services that come out from carbon cycle science. So I ask Dominik Brunner to come on the stage. Anthropogenic emissions from industry, traffic, households and agriculture affect air quality and contribute to globally increasing greenhouse gas concentration. And this topic is at the heart of Dominik's research group at the Swiss Federal Laboratory for Material Science and Technology, EMPA. Thank you, Dominik, for telling us today about the existing future application based on modeling atmospheric composition.
Thank you very much. So welcome also from my side. So I will talk about the estimation of emissions from atmospheric observations, which is one application which is evolving rapidly of atmospheric observations. And I will show you a little bit how we can use that and develop that towards services for climate change mitigation. So basically for all environmental problems where the atmosphere plays a role, we need reliable emission information. There you see here climate change, the protection of the ozone layer, air quality. We have these international treaties like the Paris Agreement, the Montreal Protocol, or the Gothenburg Protocol. They all require from the countries to report emissions, to collect information about their emissions, report that, partly also from industry. And there's also increasingly interest for instance, from cities to collect information about their emissions because they would like to reduce their carbon footprints and would like to have reliable information on where they stand and where they go. So where can we provide information from atmospheric observations, or what do we need to provide to be useful for policymakers and inventory builders? So on one hand, we should produce estimates of total emissions on a political unit, for instance, for a country or a city. Inventory builders, policymakers are also interested not only in the total, but also in the share of different sectors. So what is the contribution from traffic versus residential heating, from cows versus manure, from landfills, and so on. And something that atmospheric observations are very good at is detecting of unknown sources, which are obviously not in the inventories. For some species, especially for instance for CO2, a lot is emitted from hotspots. CO2 in Europe is emitted 50% from stacks, from power plants. So if you can quantify those, you will already go quite a long way. And then, of course, we are interested in tracking changes over time, for instance, between reporting periods in the future, between the global stock dates of the Paris Agreement, for instance. So, but how can we use atmospheric observations to quantify emissions? So basically, we have two options. One I call mass balance, and the other one inverse modeling. So here's a simple example in the upper right figure shown where an aircraft was flying around a source and measuring the concentration of a gas upwind and downwind of the source. And by multiplying the concentrations with the winds, you get fluxes, and you take a mass balance, so basically quantify the flux divergence within that volume. So that's basically, you don't need very little model information or none. You need information about wind and measurements of concentrations. That's also something you can do quite nicely with satellite observations, where you have satellite total columns up and downstream of a source. The other approach is inverse modeling. You have a measurement network or satellite observations that take observations of concentrations at specific points, and then you use an atmospheric transport model that establishes the link between concentrations and emissions upstream. So what signal would be produced by an emission source at a given location at the measurement points. And then you combine this information with a mathematical framework, a Bayesian inversion, to estimate the best emissions X or state vector X that when you apply it to the model produces model simulate concentrations that are close to the observations. So, and we have satellite observations, we have in situ observations, we also have other types of observations, ground-based remote sensing, for instance, and they come with their pros and cons, which I tried to summarize here very briefly. So satellites, we heard that before, have basically global coverage. A nice thing is also that you measure a large volume of air and not just a small point somewhere near the surface. We get increasingly satellites that are able to image. We go to high resolution and we start resolving plumes of individual sources. And that's certainly also the future. And data access certainly is also an advantage. The limitations is the limited temporal coverage. We also are limited by clouds or only daytime measurements in most cases. We can measure actually only a small number of the species reliably. Another disadvantage is certainly the comparatively low accuracy and difficult to quantify accuracy. It's not so easy to calibrate a satellite observation. The ground-based in situ, we have high temporal resolution. We can measure day and night under cloudy conditions. They can have high accuracy. We are measuring near the surface, near the sources, and have therefore strong signals. And we can measure a large number of species, basically everything we would like to measure. But measurements have poor spatial representativeness. We measure at a point which might be strongly influenced by things that's going around just in the surroundings. A major problem is certainly the sparsity. We've heard that before. For instance, in the tropical regions, we have very poor network coverage. And then we also have a diversity of networks and instruments, so that makes it more complicated to use it. We have varying data quality of these networks. So let me start now with some examples of where atmospheric observations have been successfully used to quantify emissions. And I start here with an example of emission estimation of the CFC11. You know that's one of the major compounds contributing to the depletion of the ozone layer, and therefore it had been banned under the Montreal Protocol. And so we were expecting that emissions would go down with time, because there are still remaining banks, old refrigerators with containing CFC11, for instance, along that blue line, the blue shaded area. We can take atmospheric measurements. This is a very long-lived species. We can measure at a few points on the globe, and that's sufficient to quantify the total mass of CFC11 in the atmosphere. And then we can track the changes with time, and we know the sink, it has a lifetime of about 50 years. And for that, we can estimate the emissions year by year. And that's this blue line that is shown here. So that's estimate of global emissions of CFC11 from atmospheric observations. And then we saw something unexpected, because it's forbidden, that in 2012, suddenly the emissions increased again. So something happened that should not have happened, and there have been 4 major publications on this topic, first by Steve Monska from NOAA, who really showed that there's a problem, that there's emissions that are not allowed. Rigby then looked at what region of the globe are contributing to that, and then there were 2 more papers showing that actually action was taken. And once these publications came out, obviously those causing those emissions were getting afraid and tried to reduce the emissions again. So, using atmospheric transport models, we can not only check the total emissions on the globe, but we can also allocate those emissions spatially. And using measurements at Gozan and Haterumua Island, and combined with atmospheric transport simulations, we could show that these emissions were mainly released from China. And there was little emissions before this 2012 period, then a significant increase from 2014 to 17 in the middle, and then a decrease again later on. So that was clearly assigned to not allowed emissions in China. We had, several years ago, we had another example of HFC-23, which is a very strong greenhouse gas, which is only a byproduct of the production of HCFC-22, which is used to produce Teflon. And we could show that actually the emissions reported in Europe are way too low. Especially Italy was reporting almost no emissions. And we could show that there's especially a factory in northern Italy producing Teflon, which emitted quite a lot. Whenever the transport of air towards Jungfraujoch was coming from that region, we saw high peaks in HFC-23. So that's first examples. Now I go more a little bit to policy relevance. So this is in context of Kyoto and the future Paris Agreement, Switzerland and all other countries, parties of these agreements, have to report their emissions. Here, as you see, an example of Switzerland's greenhouse gas emission inventory. And the pie chart in the middle shows the contribution of the different gases, greenhouse gases, to the total emissions. So CO2 is more than 80%. Methane contributes about 11 in CO2 equivalents, N2O 5%, and then there are these synthetic gases. But if we look on the right-hand chart, that shows the uncertainties. So total Swiss emission inventory has a certain uncertainty, which is contributed by the uncertainties of the individual gases. And here it's not CO2 which is dominating. We have fuel statistic, which from those we know the CO2 emissions very accurately. But those of methane and N2O are much more uncertain. And they dominate the uncertainty budget of the Switzerland's greenhouse gas inventory. And that's why we would like, if we want to support our government in improving the inventories, we should specifically look at these species. And so that's what we have done or are doing. So we provide, my colleague Stefan Henne is calculating year by year total Swiss emissions of methane and N2O. We have a few observation sites like the Perromünster, where Markus Leuenberger is taking measurements, and a few more stations. We use FlexPath Cosmo as a transport model, to calculate the source sensitivities, a Bayesian inversion framework to estimate annual emissions. And we do that since quite many years. And here you see figures which are in the annex of the Swiss National Inventory Report. Switzerland is one of only 2 countries worldwide, or maybe 2.5 countries worldwide that are doing that. We see the green line, that's the official reported numbers of methane in the top and of N2O emissions at the bottom, about 200 gigagrams or kilotons per year of methane emissions from Switzerland. And then since 2013, we estimate also top-down from these atmospheric observations emissions. That's the orange line. We see some year-to-year variations in our estimates, but overall we are very close to the bottom-up numbers, so the official numbers. And the same is surprisingly also true for N2O. You see this large green uncertainty bar, that's from the national inventory, which says we know that N2O emissions only with an uncertainty of 40%. And we show with our observation-based estimates that, yeah, probably we're quite good with those estimates. So that was at Swiss level. There's also activity at the European level. There was a large project which is still in its in final phase, the EU project verifying greenhouse gas emissions. So we have the 2 components on the top left. That's the official inventories reported to UNFCCC. On the right-hand side, what we try to do from atmospheric observations, not only methane and N2O, but also CO2 from fossil fuels and from land use sector are estimated. And so that's a big program where we look at these species and try to reconcile the bottom-up and top-down estimates. And I'm just picking out small examples where I contributed. So was a publication by Roxana Petrescu, the consolidated European synthesis of methane and N2O emissions for EU 27 plus UK since 1990. And it's a bit small, probably for your eyes. So actually what she has done is to collect information from many different bottom-up inventories, top-down estimates from various global and regional model simulations, and compared how well they agree. On the EU level, the agreement is relatively good. Left is the bottom-up estimates and the right top-down. And if you also account for the natural methane emissions, then the difference is not so big. But if you look closer at individual regions, the differences get quite large, especially, for instance, in Northern Europe, there's not a very good agreement between top-down and bottom-up estimates. We are also now developing a high-resolution inversion system, taking advantage of the ever-growing density of the network. We have these ICOS in Europe. All these black points are measurement sites. They put a strong constraint on methane emissions today. We are now also moving towards city, and there's a new project, PAUL, which is European Green Deal project, where we would like to quantify the CO2 emissions of 3 cities, Paris, Munich, and Zurich, with different measurement and techniques, from eddy covariance to low-cost sensors to remote sensing instruments and high-resolution modeling and so on. But this is just starting. So final words a little bit on satellite observations. That would be a big story, but I would like to pick out one interesting study from the Harvard group of Daniel Jacob, where they made an inversion of global methane emissions using observations from both TROPOMI and GOSAT, 2 different satellites. And here the lower figure here shows seasonal differences in the mean methane concentration from these satellites. So blue is TROPOMI measures less methane, red is TROPOMI has more methane. And there's considerable differences. One sigma standard deviation is 10 ppb. And if they compare that to the WMO compatibility goal of 2 ppb, that's quite a large number. And that results in quite large uncertainties in the top-down estimates. So we see here that the ratio between posterior and prior emissions, blue means posterior is lower, so TROPOMI-based estimates are lower than the EDGAR prior. If you look at Brazil, for instance, you see completely opposite results for the 2 satellites. So there's still quite large regional biases in the satellite observation, which can screw up the total estimates. We are now also looking more at individual plumes from power plants and cities. I'm skipping that and like to conclude. So I started with what are the needs of inventory builders, estimates of total emissions in political units, source attribution, and so on. I think I've shown quite good examples. Something where we can still improve is source attribution, relative share of different sectors, separation between natural and anthropogenic emissions. Really need to improve that. But for the other point, quantification of hotspots, we are taking large step also with the new satellite CO2M. Changes in recent years. In Verify, we look at long-term 20-year timescale changes. But we are, still have major challenges. We need better coverage of in situ, better quality of satellite observations, sectoral emissions, and especially also standardization of estimation procedures. So far, we have a lot of kind of research grade estimates, but we need to make a step forward to be policy relevant. We need standardization of the methods, and that's where we need to go. Yeah, thank you.
Thank you, Dominic. Let's move to the questions right away. Tom Peter asks, CFC 11 emissions, bottom-up estimated versus top-down measured, seem to not agree with each other even after subtracting the forbidden emission from Eastern China. Why? Is it not only the Chinese ignoring the Montreal Protocol?
Yeah, it's probably not only the Chinese.
Okay.
But we still see also in Europe CFC 11 emissions. It's expected that there are some remaining, but maybe we have underestimated the banks. So the CFC 11 might be still in more devices than we thought. But we also at Jungfraujoch we see peaks of CFC 11. They are decreasing clearly, but it's not just China. Yeah. But China was really contributing most to that.
Okay. While waiting for another question to come in, you jokingly said it's 2.5 countries worldwide that use this kind of methodology for their NDC reporting. What would it take, in your opinion, to boost the uptake of this methodology? I know WMO is trying to promote the concept of the IGIS, and yeah, I'm wondering what you think should be done that countries would promote such technology.
Yeah, I think on one hand you need the measurement infrastructure. Switzerland is relatively small, 1, 2, 3, 4 sites. This is not sufficient, but it's quite good already. Germany is building up with this in framework of ICOS, and I'm pretty sure they will go into that direction. Maybe in a few years we will see that as well. UK has a good network. That's the other country next to Switzerland that is doing that. So first of all, the measurement network. The other thing is that you need to convince the inventory builders that it's really useful. And in Switzerland, we have this strong collaboration with the BAFU, and we learn from each other, and I think it has been a beneficial process for both of them. And that's also the small country of Switzerland, I think, facilitates this dialogue. We know the people there. It's a small community comparative to another country. I think that's the other challenge that needs to be taken, that you need to have the people that understand that this can be really something useful, because they have their obligations, and this is an extra thing. And the BAFU is very much science-oriented also. This supports research projects, which is by far not the case in all the countries.
Okay. A question from the audience right here. Does not seem to be the case. So thanks again, Dominic, for your contribution.
At this point in time, we would like to thank again actually all the speakers of this carbon cycle session. A few questions could be answered already, however, I am convinced there must be lots of further questions around, and this brings us to our next point in the agenda. As announced earlier, this is now the time to directly interact with our speakers online. We encourage you to visit the speakers in the foreseen Gather Town room. It is just outside the main conference hall on the left side of your screens. For any questions, please see the help desks. They will help you immediately. We meet again here in 20 minutes time. This is at, let's say, 20 to 4. And yes, enjoy the time and interact with the speakers. See you soon.
Hello and welcome back after this short break. I hope you had a chance to meet the speakers and interact with them and sort out questions that didn't get answered after their talks. We will now move to our first interactive synthesis discussion, and I give the floor to Han Dollmann, so please take it away from here.
Okay, thank you. I will start to moderate this question, but it apparently means that I have to ask some questions first to the previous 4 speakers. So I'd like to ask them first to sort of give us perspective on what they consider to be the most important observation that needs to be taken globally in the next 5 to 10 years. Single observation. And you may say, well, it needs a little bit more, but I'd like you to try to focus on what's really missing at this point. And I see Benjamin already thinking about this. So maybe it's good if you could start.
Right. So my thinking goes in the direction of trying to understand spatial heterogeneity of the responses, also as I've mentioned in my talk. And so this is really getting at moving beyond sort of using remote sensing data of the Earth at the level of just providing structural information, but we need to understand how physiology responds to stresses and therefore how the carbon cycle responds to stress, climatic stress from climatic extremes, and how these responses vary across the landscape. I think this is thus far largely unknown, and information is contained in the remote sensing data, but it's not effectively used. So by just using information about greenness indices, we're not getting at this information. And so I guess it's not about taking additional measurements, but making better use of existing data that is there.
Okay. That sounds like a good answer to me. I will go to you, Marcus, first.
Okay, I would like to make 2 points. One is actually in the direction Dominic talked about. So the combination of measurements that already exist, so in situ measurements, vertical column measurements from the ground, and combine that with satellite measurements, because that has not been used to the extent that they can be used. And the second point is...
So also no investment in new measurements?
Well, at a certain point, certainly. For instance, what are strongly missing is the link between satellite and in situ measurement. So vertical profiles that should be improved either by, for instance, airplane measurements or drone measurements, because you don't have to get up to 10,000 meters or so. And there is a new method also approaching with the so-called air core measurements, lifting up a long column to the stratosphere.
And what you're saying is that those are relevant for linking up the in situ measurements also with the column-wide.
That's correct, because
satellite.
these vertical profile measurements can be done with high precision. And that is often missing when you compare satellite measurements with the high precision in situ measurement. And the second point is related to the concept I have presented about this combination of CO2 and O2 measurements, especially at those sites where I try to show where most of the changes will occur in future. So in the ocean region, the equatorial Pacific, and on land regions in Asia and in Africa.
Okay, so the other thing is that you say you first you'd like to make the link closer to in situ measurements and the satellites by adding more information about the spatial distribution, and for the rest you say specifically for your measurements, but you can probably take that a little bit wider, is to go to the areas that are currently seriously undersampled and are playing a large role in the carbon cycle. We need to improve in our measurements there. And those are in situ measurements to a large extent, what you're saying.
Yes, exactly. And mainly in Africa, there are quite a lot of dark spots, actually. So investments there would be nice.
Okay. Jens, on the soil.
Yes, on the soil, for me, it's clear that that we need to have better data on the groundwater table of drained organic soils, peatlands, because it's known that these managed organic soils are a very big net source, mostly of CO2, also of N2O. And it's also known that currently this source is mostly allocated in Southeast Asia. But what's really missing is, I mean, with this groundwater level, one can quite fairly well estimate the CO2 and methane balance of those systems, and the groundwater data are often missing. And I'm not a remote sensing person. I'm not sure whether this can be done also from remote, but certainly ground measurements, groundwater gauges are needed. It's also quite some spatial resolution to get a better idea about the water situation in these fields.
Okay. Yeah, groundwater measurements, as far, I mean, they are an ECV. Groundwater is an ECV, and the groundwater measurements you can do from satellite are the ones that you do by GRACE, and they are very much related to large areas, which is probably not good enough for your purpose. So you would have to rely on more in situ measurements or model exercises.
Yes, particularly
with hydrological
because
models. Is that correct?
Well, with models, I think it's also possible with models, but you need to have some driving data, and the overall flux size as well as the balance between CO2 and CH4 is determined by plus minus 20 centimeter water table. It's a very small range that determines what the system, in which direction it goes. And there the data is really missing. And the second point would be, because we have all those vegetation fires also there, which are partly fueled by the vegetation, but also partly fueled by the peat itself, what the peat contribution itself is. This is also quite uncertain.
Okay, thank you. I think that's quite clear. I mean, so far, none of you has said, I want this spectacular new measurement that is lurking on the horizon that we really need to invest on. You all say, well, we need better quantification of what we already have, making more clever use of it, and maybe extend it a little bit to what we have. So I'm relying on Dominic now to say whether the future is really bright for a nerd or not.
And I think we know which are the greenhouse gases. We know which are the major. Oh, sorry. We know which are the major greenhouse gases, and we can measure all of them, but with varying success and coverage. And one species we are not so good, which plays quite an important role, is N2O, where I think we could certainly expand our measurement capability. It's also one of the species we are not very good at. Well, we cannot really measure from the satellite, at least not in a way we can methane or CO2. So better measurement integration in situ networks. That would be maybe one thing I would a little bit put more emphasis on, and the other thing is certainly the global coverage. We have excellent data measurements in Europe and so on, but if we want to diagnose the state of the globe and take it serious with the global stocktake and contribute from atmospheric observations, we need to go to places where we don't have measurements yet. And the satellites can certainly help, but not always, especially in the tropics with a lot of cloud coverage. We still have problems. So that's a challenging thing, but I think we all know it.
Yes. But let me continue on that line, because you said that Switzerland and the UK are the only two countries at the moment that incorporate observation-based information. When I looked at your graph on N2O, it showed that your uncertainty ranges were at least half of the ones that are being used in the IPCC. So why do countries not jump to that and say, well, okay, apparently these guys can do a lot better job than I in terms of uncertainty, because the bias was also relatively small, if I remember. Why didn't that happen?
You mean that these
I think
estimates would be taken up?
Let me put the question slightly different. If you want to show the relevance of observation-based estimates in greenhouse gas reporting, there are two things I think that allow you to convince inventory agencies. One is you get the average right, you get the mean right, and the second one is you reduce the uncertainty. I think with N2O you've already shown that that's possible. So how is that discussion going then?
Yeah, the N2O is quite impressive. It's a bit more challenging than other species, because N2O emissions are not continuous. So there's the agricultural practices which determine at what point in time, but it was still sufficiently, it was still successful to get inversions. I'm not quite sure whether our uncertainty estimate is so robust. I think we need to have a bit more systems. If you have one system, you end up with an uncertainty range from the Bayesian inversion, but usually we know that when you have 3-4 inversion systems, the uncertainty gets a bit larger. I think there we need more, and that's what we do in Verify, to have multiple models applied to the same problem. And then when we can show that this is really, we can reduce the uncertainties, or we can tell the inventories that you're probably underestimating, that's extremely important and useful for the inventories. We have done that, for instance, also for HFCs. We see that HFC 134 emissions in Switzerland are most likely overestimated, and currently we are in a discussion why that is the case.
So you know that I was involved in Verify.
Yeah. Maybe I'm putting it too optimistic.
And in fact, if you take all the different measurements and the different top-down and bottom-up estimates, you also see a great reduction. And those UNFCCC estimates and the IPCC-based estimates just produce an enormous uncertainty, which you don't reproduce using the science-based or observation-based methods. But we're still not really at the stage where we can convince them. And I think two questions related, and maybe you have an answer to this as well. One is, how would we approach convincing, say, the reporting people in our countries who always prefer to report less rather than more, and have not necessarily the science evaluation in the sense that what matters is the amount of greenhouse gas that comes in the atmosphere. What matters is how can they report in such a way that it doesn't cost them too much. That's a slightly different perspective. How can we convince them to take on some of those measurements that we're taking?
Well, I guess there's no way around to have controls on these reported emissions. That means that we have to take additional measurements, and they are existing now. And this monitoring of the greenhouse gases as well as additional measurements need to be continued. And in the sense that if too low values would be reported, that we can detect it, as demonstrated by a couple of examples shown by Dominik Brunner. That's very important. However, it is quite difficult when you look at patchy emissions, like in the case of N2O. It gets then quite difficult. For CO2, where we have quite a good knowledge about the hotspots, it's easier, and we improve, or the modeling people improve a lot our understanding of how the emissions are then transported and mixed into the atmosphere, that the concentration measurements can correspondingly well be interpreted.
I've got to put that question back to Dominique, because I remember one of his last remarks was not quite in agreement with what you were just saying about CO2 being easy.
Now, CO2 is certainly, if we want to quantify, let's say, anthropogenic emissions to a level that is useful for inventories, that's very challenging. I think the main interest is still in looking at the natural carbon cycle, or maybe land use, land change. There's much more uncertainties where we can contribute. From fossil fuels, I think, at least for countries that don't produce fossil fuels themselves, like Switzerland, from import-export statistics, we can quantify that very well.
But still, in early 2026, we will have a Copernicus monitoring service that provides separate estimates of the emissions from fossil fuel and those from the biosphere.
Yeah.
That's in 4 years' time.
Yeah, well, CO2 emission has not just the country level as it's an objective, but also looking at cities, and therefore there is, I think, certainly scope. Cities have policy measures which are often quite independent of what is going on at the country level, and they are also interested in estimating their emissions. And there, certainly for larger cities, the satellite mission will have potential. The other thing is that these point sources, we hear what's reported, but we also see smelters in Russia or whatever that come a little bit with surprise how large the CO2 emissions are from these systems sometimes. But what I wanted to say is an important step that we need to make that it's better taken up, I think, is one point that I mentioned, the standardization. We need to go from a research grade to something like the IPCC guidelines. They have clearly defined procedures how to estimate emissions and for the different sources, and we need to have a similar system for measurement-based estimation, that we have a set of tools which have been benchmarked, which have been proven and compared and quality controlled, and then those applied to estimate emissions, that we can build trust into the numbers that we produce.
And who does the quality control and the benchmarking?
Under the lead of WMO, as I think that's for me relatively clear.
And does GAW and GCOS do enough at the moment to make that happen? Is there enough drive within the system to?
That's there can never be enough drive, but
Does there need to be more drive?
Yeah, I think so. One thing that I think we are suffering is that our transport models, we run transport models, but we have no good ways of quantifying uncertainties in the transport models. And so one thing that I also wanted to propose is to maybe develop a new tracer release experiment at large scale that we can use to benchmark transport models, which then we need kind of like calibrate it. We need to trace back things to SI units or whatever, but our transport models, they can have systematic errors which we cannot really quantify at the moment. And that's one part of the problem, that we have this uncertainty which we are struggling to reduce. And that's maybe one point that
okay. I think we need to go a little bit now on the ground. And Benjamin, in terms of you're facing to some extent the same problem. I think when you want to do ecological forecasting, what is your plan to convince agencies and governments to make use of those forecasts?
Sorry, I was muted.
Yeah.
To make use of such forecasts, the forecasts need to be available in the first place. Thus far, there's very little available and systematically updated, of course. And then, of course, like it's an opportunity to show that by repeated update and validation cycles, that these forecasts can actually be useful. So I guess like there's still much to be done in this direction.
Okay, so it's early stages in your case.
Yes, I guess like this is very much in early stages. That's also a reason why I have not been able to draw from much published research in the presentation that I showed.
Okay, thanks. In terms of net emission scenarios, how do you operate your research? Do you operate your research from the perspective of, I think this is really the critical component that we need to look at if we want to make the claims? Or do you say, there's so many claims, I think you started a little bit with that, there's so many claims around that are not based on proper science and proper observations, and we need to correct that picture? Or do you really think that we need to sort of move into the system where you can get a positive reply into the nets? I wasn't quite clear when I heard your presentation about that. And you have a short amount of time to answer this question because the sign has been shown.
Okay, so the nice thing with the net is, or with the remaining emissions that must be compensated, that the number is rather small as compared to the overall emissions. So it's a reachable target. But I'm skeptical that we can fit it with sequestration, for example. And it a bit attracts also the attention too much and too much away from reducing the fossil emissions. So there's so much discussion about the nets because it's in a way needy because we fail to reduce fast enough, and then the burden is on the net. But this is kind of the potential, I think, is not as big as some people hope it to be.
Okay, so the time is up.
Did you check if there are any questions on the iPad?
I don't see under the synthesis any questions. I don't know whether that means that we have more time here, because I think what you're saying is an interesting thing. You say, well, nets at the moment certainly are still either very much in states of development or are promising incredible amounts, and we really need to reduce fossil fuel emissions. That's the critical thing. I wholeheartedly agree. But what worries me also is a little bit that after the net discussion, you, at least in my country, you also see now increasing discussions about geoengineering and starting up geoengineering research. And that's not a subject that we're supposed to discuss here probably, but it worries me that we sort of move on gradually into the next stage, that we first say you reduce fossil fuel emissions. That doesn't really work. It's too hard. It's too, then, okay, we have this ideal scenario where we can basically take out carbon dioxide out of the atmosphere, and we have the biosphere to work on, and there are a number of other things that we can work on. And we know that that's probably also not going to work. And so we start now, all of this is not going to work. Well, we better start thinking about geoengineering and doing really sort of aggressive things to the Earth system, like putting up aerosols and other things. That's good. Would you agree on that picture, or do you think that's too pessimistic?
Certainly we have to strengthen really our intent to decrease the fossil fuels. That's certainly the first step, but geoengineering will be one part of the solution, I guess, to what we are talking about. Mainly when we look at, for instance, the air traffic or the emissions of methane. That also contributes to that. So we have to get a handle on that as well.
But that's more mitigation, isn't it? It's more in the classic sense. Dominique?
Yeah, my worry is exactly the same, that the more we talk about this solution, geoengineering and so on, this is kept in the minds in the brains of the people and of the politicians, and they think, well, we just need to wait along. The people at ETH, they are so clever, they will find the solution to all our problems. I think that's really also my worry, that the more we talk about, I see certainly some potential for, well, new technologies, but it keeps in the minds of the people that this will be the solution.
Okay.
And
I don't want to end on this depressing note. So the positive note is that when I asked all the four speakers about whether we were taking the right observations, the general answer was yes, but we need to make better use of them, and we may need to harmonize them a little bit more with the in situ and satellite. I think that's a fair point to take with us also in the writing of the next implementation plan when we look at that. And I personally would like to talk further with you about the definition of our soil carbon ECV in GCOS, which has always been a bit tough to implement, but it might become more and more important as well. So I think we sort of finished.
Yeah.
It's up to you now. I don't see any questions.
That's good.
On the,
Thank you very much. Let's give the panel a hand. Thank you very much, Han. Well done.
Thank you.
So with that, we are already quite advanced in today's program. We hope you still feel comfortable here in the meeting room for the speakers, and at home at your desks or dining tables, or maybe you moved on to sit on your sofas or couches. But it's not yet time to get offline, since there is one important last item on the agenda.
Yes, apart from the live program here in the main conference hall, we also have a virtual poster exhibition in a room next to this one, again on the left-hand side on your screens. Our poster presenters have also prepared a short poster pitch, which will follow here on this live stream shortly. After that, the presenters will wait in front of their posters and wait for your questions and inputs.
And also our conference room, our virtual conference room, will stay open until, say, 5:30. Please feel free to have a chat with whomever you would like and have a glass of wine or an unalcoholic beer. next to you. With this, we say goodbye for today and look forward to seeing you all again tomorrow. Our program starts at 9 o'clock sharp. So we wish you an enjoyable and nice evening.
Hello. With our poster, we want to present the project Harnessing the Power of Crowdsourcing to Tackle 21st Century Mountain Observation Challenges. The main question is, how can observations taken by citizens in the mountains contribute to the professional monitoring systems by GLAMOS, the Glacier Monitoring Observation System, and PERMOS, the Permafrost Observation System. Our project shows you how we assess the user needs, how the system is defined, how we implemented the whole platform infrastructure and the user needs, and what are the next steps to achieve an integration of the observations into the monitoring services. If you want to join and if you are interested, have a look to our website or join our observation campaign. Thanks a lot.
Good morning, everyone. My name is Simone Brunamonti, and I'm presenting the work we did at EMPA on the absolute validation of a balloon-borne spectrometer for water vapor measurements in the upper atmosphere. So here we have an instrument developed to fly on board meteorological balloons and measure water vapor in the upper troposphere and lower stratosphere, meaning the region of altitudes between 8 and 25 kilometers approximately. Water vapor is a strong greenhouse gas, and this development addresses the need for a replacement of the currently used reference technique for in situ measurements of this essential climate variable in long-term monitoring networks such as GRUAN, the GCOS reference upper air network. We have recently validated our spectrometer in collaboration with METAS, the Federal Institute of Meteorology, using SI traceable reference mixtures of water vapor at UTLS relevant conditions. So this is what you will find in the poster. Thanks for your attention, and I hope to see you later for questions.
Good afternoon. In this poster, we present our project that aims at safely archiving and digitizing the sunspot observations obtained at the Specola Solare Ticinese in Locarno since 1957. The sunspot number allows to quantify the solar activity, which is highly correlated with the total solar irradiance variations. The sunspot data series is long more than 400 years, and it allows to reconstruct the solar irradiance variations back in the past. All collected observations are being archived and digitized at the university's archives at ETH Zurich. The digitized observations are being published on the Manuscripta portal. In parallel, we are completing and publishing a sunspot group database. Data from 1981 to now are already online.
Hello, I'm Stefan Naiki from the PMOD WRC in Davos. I'd like to give you a short overview of the GCOS Switzerland project called EXTRAC. This stands for Extending the Calibration Traceability of Long-Wave Radiation Time Series. In this project, we're mainly interested in developing a method to retrieve original data from the BSRN archive of ground-based radiation measurements. There are a number of reasons why original data is no longer available at some stations. For instance, BSRN archives time series of important parameters, but not the raw data. In addition, advances in information technology have often meant that old archives are not transferred to new ones. The EXTRAC project aims to find a method to recover raw long-wave radiation data from the BSRN archives. Please come and visit our poster to find out more. Thanks and see you there.
We present our newly developed instrument for the continuous semi-online monitoring of carbonaceous aerosols, developed with support of the GAW CH science program. The instrument has been tested in a diversity of sites, from urban locations to the Jungfrau Observatory above the planetary boundary layer. It is very stable. In almost 1 year of unattended operation at the Jungfrau, we did not experience loss of data due to instrument malfunction. The low limit of detection of 0.1 micrograms of carbon captured in the filter makes it the most precise instrument of its kind. Furthermore, convenient unique features make the instrument stand out during day-to-day operation or for scientific purposes. Its fast thermograms help identify aerosol sources, for instance, differentiating between local fossil fuel emissions from long-range transport of plumes originating from California wildfires. We are happy to answer questions or give more information. Thank you for your attention.
Water vapor is the strongest natural greenhouse gas and feeds back to climate warming. Its concentration is monitored with high vertical resolution up to the lower stratosphere by balloon-borne frost-point hygrometers. The freon cooling agent they use will not be available soon, in consequence to the Kigali Amendment of the Montreal Protocol. Peltier cooling provides an alternative. My poster reports on the progress of our development of the Peltier-cooled frost-point hygrometer, PCFH. We present design changes to overcome recent problems. A novel frost-point identification scheme is used in the comparison flight from August 24 this year. It was carried out with the reference instrument CFH by our colleagues from the German Weather Service DWD in Lindenberg, Germany. The results look very promising, and I would be happy to show them to you at our poster.
Hello everybody, my name is Christoph Zellweger from EMPA Dübendorf. I am responsible for the World Calibration Center for Surface Ozone, Carbon Monoxide, Methane and Carbon Dioxide, which is one of the central facilities of the WMO GAW program. The aim of our work is to have quality assured data which are traceable to the references that we have in the GAW program. My poster will give an overview of our activities, which are mainly system and performance audits at Global Atmosphere Watch stations. Furthermore, the World Calibration Center cooperates with QSX Switzerland and other partners with regard to capacity building, training and twinning activities. I just returned last week from a mission to Mount Kenya, where colleagues of Meteo Swiss and I myself trained station staff, and we did some maintenance work and quality checks. Thanks to this work, we now have data series from a very data-sparse region of the world. If you want to know more about our activities, please come and visit my poster. Thank you.
Hello, everybody. My name is Martin Steinbacher from EMPA in Dübendorf. EMPA hosts two of so-called central facilities in support of WMO's Global Atmosphere Watch program. And this poster introduces one of them, which is the Quality Assurance Science Activity Center, Switzerland. The poster first gives a short introduction to GAW's overall quality management framework and then focuses on the 4 core areas of activity of QSX Switzerland, which is research, capacity building, training and twinning, contribution to GAW outreach, and cooperation and networking with other programs and projects. If you want to know more about the activities and achievements of QSX Switzerland, please come and see my poster later today.
Hello everyone, my name is Manu Mailleux. It is my pleasure to contribute to the GAW GCOS Symposium with a poster entitled The Multi-Decadal FTIR Monitoring Program of University of Liège at the Jungfrau Station. The aim is to provide you with a brief description of the FTIR technique and the instrumental setup in use at the Jungfrau Station, to portray our monitoring effort and, more importantly, to present an overview of the geophysical products that are available. Sample time series are shown, and I will be more than happy to give more details about them and to exchange with you during the Monday session. See you soon at poster 10.